Chapter 1. Rational Numbers. Rational numbers. A number which can be expressed in the form of p upon q, where p and q are integers and q is not equal to 0, is called a rational number. For example, 4 upon 9 minus 3 upon 7 minus 5 upon 3 minus 1 upon minus 9 and 9 upon minus 7 are rational numbers. Positive and negative rational numbers. A positive rational number has both the numerator and the denominator either positive or negative. For example, 6 upon 7 and minus 5 upon minus 11 are positive rational numbers. A negative rational number has either the numerator or the denominator negative. For example, minus 3 upon 7 and 9 upon minus 4 are negative rational numbers. Absolute value of a rational number. We know that the absolute value of an integer is obtained by taking only the numerical value of that integer. For example, absolute value of 3 equal to 3 and absolute value of minus 3 equal to 3. In the same way, we can find the absolute value of rational numbers. Example, absolute value of 2 upon 5 equal to 2 upon 5 and absolute value of minus 2 upon 5 equal to 2 upon 5. Thus, the absolute value of a rational number is its numerical value regardless of its sign. Standard form of a rational number. A rational number p upon q is said to be in its standard form if the denominator q is positive and integers p and q have no common factor other than 1. Let us find the standard form of rational number 16 upon 20. We find the HCF of 16 and 20, which is 4. Now divide numerator and denominator by 4. 16 divided by 4 upon 20 divided by 4 equal to 4 upon 5. 4 and 5 have no common factor other than 1. Hence, the standard form of 16 upon 20 is 4 upon 5. Equivalent rational numbers. Two rational numbers are said to be equivalent if they have the same standard form. For example, 2 upon 3 and 8 upon 12 are equivalent rational numbers, as 8 upon 12 can be written in the standard form as 2 upon 3. Note, we can find the equivalent rational number of a given rational number by multiplying or dividing the numerator and denominator by the same non-zero integer. Methods to check the equality of two rational numbers. Method 1. Convert the given rational numbers in their standard form. If the standard forms of two given rational numbers are equal, then the given rational numbers are equal. For example, rational numbers minus 15 upon 40 and minus 24 upon 64 are equal. Let us verify it. Standard form of minus 15 upon 40 is minus 15 upon 40 divided by 5 upon 5 equal to minus 3 upon 8, dividing both the numerator and denominator by the HCF of 15 and 40, that is 5. Standard form of minus 24 upon 64 is minus 24 upon 64 divided by 8 upon 8 equal to minus 3 upon 8, dividing both the numerator and denominator by the HCF of 24 and 64, that is 8. Hence, minus 15 upon 40 equal to minus 24 upon 64. As both the given rational numbers have the same standard form, they are equal. Method 2. If p upon q and r upon s are two rational numbers, and p into s equal to q into r, then the rational numbers are equal. For example, rational numbers minus 7 upon 9 and 14 upon minus 18 are equal. Let us verify it. Minus 7 upon 9 and 14 upon minus 18 equal to minus 7 upon 9 and minus 14 upon 18. Writing both the rational numbers with positive denominator. Minus 7 into 18 equal to minus 126. Numerator of first rational number into denominator of second. Minus 14 into 9 equal to minus 126. Numerator of second into denominator of first. Minus 7 upon 9 equal to minus 14 upon 18. As minus 7 into 18 equal to minus 14 into 9 equal to minus 126. Comparing and ordering of rational numbers. To compare two or more than two rational numbers, we follow the given steps. Make all the given denominators positive. Take the LCM of the denominators. Now convert the given rational numbers into equivalent rational numbers with common denominator. Compare the numerators of rational numbers. The number with greater numerator will be greater. Let us compare and arrange the following rational numbers in ascending order. Minus 4 upon 7, minus 9 upon 14, 13 upon minus 28, minus 23 upon 42. First, write the given rational numbers with positive denominators as follows. Minus 4 upon 7, minus 9 upon 14, minus 13 upon 28, minus 23 upon 42. Now find the LCM of 7, 14, 28 and 42. LCM of 7, 14, 28, 42 is 84. We have minus 4 upon 7 equal to minus 4 upon 7 into 12 upon 12 equal to minus 48 upon 84. Minus 9 upon 14 equal to minus 9 upon 14 into 6 upon 6 equal to minus 54 upon 84. Minus 13 upon 28 equal to minus 13 upon 28 into 3 upon 3 equal to minus 39 upon 84. Minus 23 upon 42 equal to minus 23 upon 42 into 2 upon 2 equal to minus 46 upon 84. LCM equal to 2 into 2 into 3 into 7 equal to 84. Now arrange the products in ascending order. Minus 54 upon 84 less than minus 48 upon 84 is less than minus 46 upon 84 is less than minus 39 upon 84. Hence, minus 9 upon 14 is less than minus 4 upon 7 is less than minus 23 upon 42 is less than minus 13 upon 28. Representation of rational numbers on the number line. In the previous class, we have learned to represent integers on the number line. In the same way, every rational number can be represented on a number line. On the number line, all negative rational numbers such as minus p upon q, p upon minus q are shown to the left of 0, and all positive rational numbers such as p upon q are shown to the right of 0. Let us represent 3 upon 4 and minus 4 upon 7 on a number line. Draw a number line OA in which O represents 0 and A represents 1. In 3 upon 4, the denominator is 4, so divide OA in 4 equal parts. Count 3 parts from O and mark the third part as P, which represents 3 upon 4. Now, draw another number line OB in which O represents 0 and B represents minus 1. In minus 4 upon 7, the denominator is 7. So divide OB in 7 equal parts. Count 4 parts from O and mark the fourth part as R, which represents minus 4 upon 7. Find the value of x in the following. Addition and subtraction on rational numbers. Addition of rational numbers. Case 1. If p upon q and r upon q are two rational numbers with the same denominator q, then p upon q plus r upon q equal to p plus r upon q. Let us add the following. A. Minus 2 upon 5 and minus 4 upon 5. B. 3 upon 7 and 12 upon 7. We have A. Minus 2 upon 5 plus minus 4 upon 5 equal to minus 2 minus 4 upon 5 equal to minus 6 upon 5. B. 3 upon 7 plus 12 upon 7 equal to 3 plus 12 upon 7 equal to 15 upon 7. Case 2. If p upon q and r upon s are two rational numbers such that q is not equal to s, then p upon q plus r upon s equal to ps plus qr upon qs. Let us add 3 upon 4 and minus 2 upon 5. LCM of 4 and 5 is 20. So, 3 upon 4 plus minus 2 upon 5 equal to 3 into 5 plus minus 2 into 4 upon 20 equal to 15 minus 8 upon 20 equal to 7 upon 20. Properties of addition of rational numbers. Closure property. The sum of two rational numbers is always a rational number. If p upon q and r upon s are two rational numbers, then p upon q plus r upon s is also a rational number. For example, minus 9 upon 10 plus minus 13 upon 20 equal to minus 9 into 2 plus minus 13 into 1 upon 20 equal to minus 18 minus 13 upon 20 equal to minus 31 upon 20, which is also a rational number. Commutative property. Two rational numbers can be added in any order, but their sum remains the same. If p upon q and r upon s are two rational numbers, then p upon q plus r upon s equal to r upon s plus p upon q. Let us verify that the addition of two given rational numbers, say minus 3 upon 4 and minus 2 upon 3, is commutative. We have minus 3 upon 4 plus minus 2 upon 3 equal to minus 3 into 3 plus minus 2 into 4 upon 12. LCM of 4 and 3 is 12 equal to minus 9 minus 8 upon 12 equal to minus 17 upon 12. And minus 2 upon 3 plus minus 3 upon 4 equal to minus 2 into 4 plus minus 3 into 3 upon 12 equal to minus 8 minus 9 upon 12 equal to minus 17 upon 12. Therefore, minus 3 upon 4 plus minus 2 upon 3 equal to minus 2 upon 3 plus minus 3 upon 4. Hence, commutative property for addition of rational numbers is verified. Associative property. The sum of three or more rational numbers does not depend on the order in which they are grouped. That is, order is immaterial. If p upon q, r upon s and v upon u are three rational numbers, then p upon q plus r upon s plus v upon u is equal to p upon q plus r upon s plus v upon u. Let us verify that the addition of three rational numbers 3 upon 4 minus 2 upon 5 and minus 7 upon 10 is associative. We have 3 upon 4 plus minus 2 upon 5 plus minus 7 upon 10 equal to 3 into 5 plus minus 2 into 4 upon 20 plus minus 7 upon 10 equal to 15 minus 8 upon 20 plus minus 7 upon 10 equal to 7 upon 20 plus minus 7 upon 10 equal to 7 into 1 plus minus 7 into 2 upon 20 equal to 7 minus 14 upon 20 equal to minus 7 upon 20. Now 3 upon 4 plus minus 2 upon 5 plus minus 7 upon 10 equal to 3 upon 4 plus minus 2 into 2 plus minus 7 into 1 upon 10 equal to 3 upon 4 plus minus 4 minus 7 upon 10 equal to 3 upon 4 plus minus 11 upon 10 equal to 3 into 5 plus minus 11 into 2 upon 20 equal to 15 minus 22 upon 20 equal to minus 7 upon 20. Therefore, 3 upon 4 plus minus 2 upon 5 plus minus 7 upon 10 equal to 3 upon 4 plus minus 2 upon 5 plus minus 7 upon 10. Hence, associative property for addition of rational number is verified. Existence of additive identity or property of 0. The sum of any rational number and 0 is the rational number itself. Therefore, 0 is called the additive identity of rational numbers. If p upon q be any rational number, then 0 plus p upon q equal to p upon q plus 0 equal to p upon q. Let us verify that 0 plus minus 8 upon 11 equal to minus 8 upon 11. We have 0 plus minus 8 upon 11 equal to 0 into 11 plus minus 8 into 1 upon 11 equal to 0 plus minus 8 upon 11 equal to minus 8 upon 11. Existence of additive inverse or negative of a rational number. For every rational number p upon q, there exists a rational number minus p upon q, such that p upon q plus minus p upon q equal to 0. Minus p upon q is called additive inverse of p upon q and vice versa. If p upon q and minus p upon q be any rational numbers, then p upon q plus minus p upon q equal to 0. That is, minus p upon q is called the additive inverse of p upon q. Let us verify that 4 upon 5 plus minus 4 upon 5 equal to 0. We have 4 upon 5 plus minus 4 upon 5 equal to 4 plus minus 4 upon 5 equal to 4 minus 4 upon 5 equal to 0. Subtraction of rational numbers. If p upon q and r upon s are two rational numbers, then subtracting r upon s from p upon q means adding additive inverse of r upon s to p upon q. Thus, p upon q minus r upon s equal to p upon q plus minus r upon s. As additive inverse, r upon s is minus r upon s. Let us subtract minus 4 upon 7 from minus 3 upon 11. We have minus 3 upon 11 minus minus 4 upon 7 equal to minus 3 upon 11 plus 4 upon 7 equal to minus 3 into 7 plus 4 into 11 upon 77 equal to minus 21 plus 44 upon 77 equal to 23 upon 77. Properties of subtraction of rational numbers. Closure property. The difference of two rational numbers is also a rational number. If p upon q and r upon s are two rational numbers, then p upon q minus r upon s is also a rational number. Let us find minus 21 upon 11 minus 25 upon 33 equal to minus 21 into 3 minus 25 into 1 upon 33 equal to minus 63 minus 25 upon 33 equal to minus 88 upon 33 divided by 11 upon 11 equal to minus 8 upon 3, which is a rational number. Property of 0. If 0 is subtracted from a rational number, the result is a rational number itself. If P upon Q is a rational number, then P upon Q minus 0 equal to P upon Q. Let us verify that 3 upon 10 minus 0 equal to 3 upon 10. We have 3 upon 10 minus 0 equal to 3 minus 0 into 10 upon 10 equal to 3 minus 0 upon 10 equal to 3 upon 10. Example. Simplify. A. 7 upon 8 minus 11 upon 12 plus 4 upon 15. Solution. A. LCM of 8, 12 and 15 equal to 120. 7 upon 8 minus 11 upon 12 plus 4 upon 15 equal to 15 into 7 minus 10 into 11 plus 8 into 4 upon 120 equal to 105 minus 110 plus 32 upon 120 equal to 137 minus 110 upon 120 equal to 27 upon 120 equal to 27 upon 120 divided by 3 upon 3 equal to 9 upon 40. Example. The sum of two rational numbers is minus 7. If one of them is minus 11 upon 3, find the other. Solution. Let the other number be x. Therefore, minus 11 upon 3 plus x equal to minus 7. X equal to minus 7 plus 11 upon 3 equal to minus 7 into 3 plus 11 into 1 upon 3 equal to minus 21 plus 11 upon 3 equal to minus 10 upon 3. Hence, the other number is minus 10 upon 3. Remember, rational numbers are neither commutative nor associative under subtraction. For subtraction of rational numbers, identity and inverse elements do not exist. Subtract the following. Multiplication of rational numbers. If P upon Q and R upon S are two rational numbers, then P upon Q into R upon S equal to P into R upon Q into S. Product of two rational numbers equal to product of their numerators upon product of their denominators. Let us multiply minus 33 upon 25 and 105 upon minus 27. We have minus 33 upon 25 into 105 upon minus 27 equal to minus 33 into 105 upon 25 into minus 27 equal to minus 11 into 7 upon 5 into minus 3 equal to minus 77 upon minus 15 equal to 77 upon 15. Properties of multiplication of rational numbers. Closure property. The product of two rational numbers is always a rational number. If P upon Q and R upon S are two rational numbers, then P into R upon Q into S is also a rational number. This property is called the closure property for multiplication of rational numbers. For example, minus 2 upon 3 into minus 4 upon 5 equal to minus 2 into minus 4 upon 3 into 5 equal to 8 upon 15, which is a rational number. Commutative property. Two rational numbers can be multiplied in any order. Their product remains the same. If P upon Q and R upon S are two rational numbers, then P upon Q into R upon S equal to R upon S into P upon Q. Let us show that 3 upon minus 7 into minus 7 upon 12 equal to minus 7 upon 12 into 3 upon minus 7. We have 3 upon minus 7 into minus 7 upon 12 equal to minus 21 upon minus 84 equal to minus 21 upon minus 84 equal to 7 upon 28 equal to 1 upon 4. So, 3 upon minus 7 into minus 7 upon 12 equal to minus 7 upon 12 into 3 upon minus 7, hence verified. Associative property. The product of 3 or more rational numbers does not depend on the order in which they are grouped. That is, order is immaterial. If P upon Q, R upon S, and U upon V are 3 rational numbers, then P upon Q into R upon S into U upon V equal to P upon Q into R upon S into U upon V. Let us show that minus 1 upon 2 into 3 upon minus 4 into minus 16 upon 9 equal to minus 1 upon 2 into 3 upon minus 4 into minus 16 upon 9. We have minus 1 upon 2 into minus 3 upon 4 into minus 16 upon 9 equal to 3 upon 8 into minus 16 upon 9 equal to minus 2 upon 3. Existence of multiplicative identity. The product of any rational number and 1 is the rational number itself. Therefore, 1 is called the multiplicative identity of rational numbers. If P upon Q is a rational number, then 1 into P upon Q equal to P upon Q into 1 equal to P upon Q. Let us verify that minus 15 upon 18 into 1 equal to minus 15 upon 18 into 1 upon 1 equal to minus 15 into 1 upon 18 into 1 equal to minus 15 upon 18. Property of 0. If P upon Q is a rational number, then P upon Q into 0 equal to 0 equal to 0 into P upon Q. For example, 25 upon 24 into 0 equal to 25 upon 24 into 0 upon 1 equal to 25 into 0 upon 24 into 1 equal to 0 equal to 0 into 25 upon 24. Existence of multiplicative inverse or reciprocal. For every non-zero rational number P upon Q, there exists a rational number Q upon P such that P upon Q into Q upon P equal to 1. Q upon P is called the multiplicative inverse or reciprocal of P upon Q. If P upon Q and Q upon P are 2 rational numbers, then P upon Q into Q upon P equal to 1 equal to Q upon P into P upon Q. Let us find the multiplicative inverse of A minus 7 upon 9. Now, A, the multiplicative inverse of minus 7 upon 9 is 9 upon minus 7. Distributive property of multiplication over addition and subtraction. If P upon Q, R upon S and U upon V are 3 rational numbers, then P upon Q into R upon S plus U upon V equal to P upon Q into R upon S plus P upon Q into U upon V. This is called distributive property of multiplication over addition. P upon Q into R upon S minus U upon V equal to P upon Q into R upon S minus P upon Q into U upon V. This is called distributive property of multiplication over subtraction. Multiply. Division of rational numbers. Division is inverse of multiplication. When P upon Q is divided by R upon S, then P upon Q is called the dividend R upon S is called the divisor, and the result is known as the quotient. If P upon Q and R upon S are two rational numbers such that R upon S is not equal to 0, then P upon Q divided by R upon S equal to P upon Q into reciprocal of R upon S equal to P upon Q into S upon R. Let us divide A 6 by 3 upon 4. We have A 6 divided by 3 upon 4 equal to 6 into 4 upon 3 equal to 8. Properties of division of rational numbers. Closure property. If P upon Q and R upon S are two rational numbers, then P upon Q divided by R upon S is always a rational number, where R upon S is not equal to 0. Let us divide minus 6 upon 7 by minus 15. We have minus 6 upon 7 divided by minus 15 equal to minus 6 upon 7 into 1 upon minus 15 equal to 2 upon 35, which is a rational number. If P upon Q is a rational number and P upon Q is not equal to 0, then P upon Q divided by 1 equal to P upon Q, and P upon Q divided by minus 1 equal to minus P upon Q. Let us divide A 3 upon 4 by 1. We have A 3 upon 4 divided by 1 equal to 3 upon 4 into 1 upon 1 equal to 3 upon 4. If P upon Q is a rational number and P upon Q is not equal to 0, then P upon Q divided by P upon Q equal to 1. Let us divide A 2 upon 3 by 2 upon 3. We have A 2 upon 3 divided by 2 upon 3 equal to 2 upon 3 into 3 upon 2 equal to 1. Divide the following. Multiple choice questions. Chapter 2. Exponents and powers. Powers. When a number is written in the form of a raised to the power n, the number is said to be written in exponential form. Here a is called the base of the number and n is called the power or exponent, and we read the number as a raised to the power n. For example, a number, say 64, can be expressed as the product of prime factors as shown. 64 equal to 2 into 2 into 2 into 2 into 2 into 2. It can be written as 2 raised to the power 6. Here 2 is called the base and 6 is called the exponent. Similarly, minus 125 equal to minus 5 into minus 5 into minus 5 equal to minus 5 cube. Here minus 5 is called the base and 3 is called the exponent. Integral exponents of a rational number. Positive integral exponent. A rational number multiplied several times by itself can be expressed in the exponential notation. Let P upon Q be a rational number and it is multiplied by itself n times, and n is a positive integer. Then P upon Q into P upon Q into P upon Q into n times equal to P into P into P into up to n times upon q into q into q into up to n times equal to p raised to the power n upon q raised to the power n equal to p upon q wholes raised to the power n. Thus, p upon q wholes raised to the power n equal to p raised to the power n upon q raised to the power n. Here n is a positive integer. Example A. 7 upon 3 into 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 7 upon 3 equal to 7 upon 3 wholes raised to the power 6, where 7 upon 3 is the base and 6 is the exponent. B. Minus 2 upon 5 into minus 2 upon 5 into minus 2 upon 5 equal to minus 2 upon 5 wholes cube, where minus 2 upon 5 is the base and 3 is the exponent. Negative integral exponent. Let p upon q be a rational number and m is a negative integer. Then p upon q wholes raised to the power minus m equal to 1 upon p upon q wholes raised to the power m equal to q upon p wholes raised to the power m. Example A. 5 raised to the power minus 3 equal to 1 upon 5 cube equal to 1 upon 5 wholes cube. B. 7 upon 4 wholes raised to the power minus 7 equal to 1 upon 7 upon 4 whole square equal to 4 upon 7 whole square. Example 1. Evaluate A. 2 upon 3 wholes raised to the power 4. B. Minus 3 upon 2 wholes cube. Solution A. 2 upon 3 wholes raised to the power 4 equal to 2 upon 3 into 2 upon 3 into 2 upon 3 into 2 upon 3 equal to 16 upon 81. B. Minus 3 upon 2 wholes cube equal to minus 3 upon 2 into minus 3 upon 2 into minus 3 upon 2 equal to minus 27 upon 8. Example 2. Express the following with positive exponent. A. 2 upon 7 wholes raised to the power minus 5. B. 10 upon 9 wholes raised to the power minus 6. Solution A. 2 upon 7 wholes raised to the power minus 5 equal to 1 upon 2 upon 7 wholes raised to the power 5 equal to 7 upon 2 wholes raised to the power 5. B. 10 upon 9 wholes raised to the power minus 6 equal to 1 upon 10 upon 9 wholes raised to the power 6 equal to 9 upon 10 wholes raised to the power 6. Example 3. Simplify and express the result as a rational number. A. 3 upon 4 square into minus 1 upon 2 wholes raised to the power 5 into 2 raised to the power 4. Solution A. 3 upon 4 square into minus 1 upon 2 wholes raised to the power 5 into 2 raised to the power 4 equal to 3 upon 4 into 3 upon 4 into minus 1 upon 2 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 into 2 into 2 into 2 into 2 equal to 9 upon 16 into minus 1 upon 2 equal to minus 9 upon 32. Example 4. Find the reciprocal of the following. A. Minus 5 cube. B. 9 upon 7 wholes raised to the power 4. Solution. A. Minus 5 cube equal to 1 upon minus 5 whole cube. B. 9 upon 7 wholes raised to the power 4 equal to 7 upon 9 wholes raised to the power 4. Example 5. Evaluate. A. Minus 3 upon 4 wholes raised to the power 0. B. 107 upon 33 wholes raised to the power 0. C. 2 cube plus 2 raised to the power 4 wholes raised to the power 0. Solution. A. Minus 3 upon 4 whole raised to the power 0 equal to 1. B. 107 upon 33 whole raised to the power 0 equal to 1. C. 2 cube plus 2 raised to the power 4 whole raised to the power 0 equal to 8 plus 16 whole raised to the power 0 equal to 24 whole raised to the power 0 equal to 1. Example 6. Evaluate. Solution. A. 4 upon 9 whole raised to the power minus 5 into 3 upon 4 whole raised to the power minus 6 equal to 9 upon 4 whole raised to the power 5 into 4 upon 3 whole raised to the power 6 equal to 9 into 9 into 9 into 9 into 9 upon 4 into 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 4 upon 3 into 3 into 3 into 3 into 3 into 3 equal to 9 into 9 into 4 upon 1 equal to 81 into 4 equal to 324. Example 7. Find the value of solution. A. 3 raised to the power minus 1 plus 4 raised to the power minus 1 into 7 upon 12 wholes raised to the power minus 1 equal to 1 upon 3 plus 1 upon 4 into 12 upon 7 equal to 4 plus 3 upon 12 into 12 upon 7 equal to 7 upon 12 into 12 upon 7 equal to 1. Express each of the following rational numbers in exponential form. Simplify. Laws of integral exponents. First law, if p upon q is any rational number and m and n are two integers, then p upon q whole raised to the power m into p upon q whole raised to the power n equal to p upon q whole raised to the power m plus n. Let us simplify. A. 2 upon 9 whole raised to the power minus 5 into 2 upon 9 whole cube. We have A. 2 upon 9 whole raised to the power minus 5 into 2 upon 9 whole cube equal to 2 upon 9 whole raised to the power minus 5 plus 3 equal to 2 upon 9 whole raised to the power minus 2 equal to 9 upon 2 square, as p upon q whole raised to the power m into p upon q whole raised to the power n equal to p upon q whole raised to the power m plus n. Second law, if p upon q is any rational number and m and n are two integers, then p upon q whole raised to the power m divided by p upon q whole raised to the power n equal to p upon q whole raised to the power m minus n, when m is greater than n. Let us simplify and express with positive exponent. A. minus 2 upon 7 whole raised to the power 5 divided by minus 2 upon 7 whole cube. We have A. minus 2 upon 7 whole raised to the power 5 divided by minus 2 upon 7 whole cube equal to minus 2 upon 7 whole raised to the power 5 minus 3 equal to minus 2 upon 7 whole square, as p upon q whole raised to the power m divided by p upon q whole raised to the power n equal to p upon q whole raised to the power m minus n. Third law, if p upon q is any rational number and m and n are two integers, then p upon q whole raised to the power m divided by p upon q whole raised to the power n equal to 1 upon p upon q whole raised to the power n minus m, where m is less than n. Example, A. minus 2 upon 7 whole raised to the power 5 divided by minus 2 upon 7 whole raised to the power 8 equal to 1 upon minus 2 upon 7 whole raised to the power 8 minus 5 equal to 1 upon minus 2 upon 7 whole cube equal to 7 upon minus 2 whole cube, as P upon Q whole raised to the power m divided by P upon Q whole raised to the power n equal to 1 upon P upon Q whole raised to the power n minus m. Fourth law. If P upon Q is any rational number and m and n are two integers, then P upon Q whole raised to the power m whole raised to the power n equal to P upon Q whole raised to the power m into n equal to P upon Q whole raised to the power mn. Example, minus 3 upon 2 whole raised to the power 5 whole square equal to minus 3 upon 2 whole raised to the power 5 into 2 equal to minus 3 upon 2 whole raised to the power 10. Fifth law. If P upon Q and R upon S are two rational numbers and m is an integer, then P upon Q whole raised to the power m into R upon S whole raised to the power m equal to P upon Q into R upon S whole raised to the power n. Example A. 9 upon 8 cube into 16 upon 15 whole cube equal to 9 upon 8 into 16 upon 15 whole cube equal to 3 into 2 upon 5 whole cube equal to 6 upon 5 whole cube equal to 6 into 6 into 6 upon 5 into 5 into 5 equal to 216 upon 125. Example 8. Find x if minus 1 upon 2 whole raised to the power 19 divided by minus 1 upon 2 whole raised to the power 8 equal to minus 1 upon 2 whole raised to the power minus 2x plus 1. Solution. Minus 1 upon 2 whole raised to the power 19 divided by minus 1 upon 2 whole raised to the power 8 equal to minus 1 upon 2 whole raised to the power minus 2x plus 1. Minus 1 upon 2 whole raised to the power 19 minus 8 equal to minus 1 upon 2 whole raised to the power minus 2x plus 1. Minus 1 upon 2 whole raised to the power 11 equal to minus 1 upon 2 whole raised to the power minus 2x plus 1. 11 equal to minus 2x plus 1 on comparing the exponents of both the sides. Minus 2x equal to 10, minus x equal to 10 upon 2, x equal to minus 5. Example 9. By what number should 1 upon 2 raised to the power minus 1 be multiplied so that the product is equal to minus 5 upon 9 raised to the power minus 1? Solution. Let the number be x. So, 1 upon 2 raised to the power minus 1 into x equal to minus 5 upon 9 raised to the power minus 1. X equal to minus 5 upon 9 raised to the power minus 1 divided by 1 upon 2 raised to the power minus 1. X equal to minus 5 upon 9 raised to the power minus 1 divided by 2 upon 1. X equal to minus 9 upon 5 divided by 2. X equal to minus 9 upon 5 into 1 upon 2. X equal to minus 9 upon 10. Note, before multiplication of two or more rational numbers, reduce them in their lowest term. Express each of the following rational numbers with a negative exponent. Scientific notation or standard form. Expressing very large and very small numbers in standard form. In our daily life, we often come across very large numbers as well as very small numbers. For example, the distance of the sun from the earth is 150 crore kilometer. It becomes difficult to remember the number of zero it has. In such cases, for conveniences, we write numbers using exponents, with base 10, that is, 150 crore can be written as 15 into 10 raised to the power 7 or 1.5 into 10 raised to the power 8. Similarly, the number 0.000000022 centimeter, which is a very, very small number, can be written as 22 into 10 raised to the power minus 9 centimeter or 2.2 into 10 raised to the power minus 8 centimeter. Writing a very large or very small number in the form k into 10 raised to the power n, where 1 is less than or equal to k, which is less than or equal to 10, and n is any integer, is called scientific notation or standard form. Example: express the following numbers in their standard forms. A. 35 lakh. B. 0.00000000082. Solution: A. 35 lakh equal to 3.5 into 10 raised to the power 6. B. 0.00000000082 equal to 8.2 into 10 raised to the power minus 10. Example: express the following numbers in their usual forms. A. 3.14 into 10 raised to the power 8. B. 4 into 10 raised to the power minus 7. Solution: A. 3.14 into 10 raised to the power 8 equal to 3.14 into 10 crore equal to 31 crore 40 lakh .00 equal to 31 crore 40 lakh. B. 4 into 10 raised to the power minus 7 equal to 4 upon 1 crore equal to 0.0000004. Example: the mass of a proton is 1.67 into 10 raised to the power minus 24 gram, and that of an electron is 9.10 into 10 raised to the power minus 28 gram. Find the ratio of their masses. Solution: mass of a proton equal to 1.67 into 10 raised to the power minus 24 gram. Mass of electron equal to 9.10 into 10 raised to the power minus 28 gram. Ratio of their masses equal to mass of proton upon mass of electron equal to 1.67 into 10 raised to the power minus 24 upon 9.10 into 10 raised to the power minus 28 equal to 16,700 into 10 raised to the power minus 28 upon 9.10 into 10 raised to the power minus 28 equal to 16,700 upon 9.10 equal to 16,70,000 upon 910 equal to 1,835 upon 1 approximately. Multiple choice questions. Chapter 3. Squares and Square Roots. Squares. When a number is multiplied by itself, the product so obtained is called the square of the number. Example: 3 into 3 equal to 3 square equal to 9. 4 into 4 equal to 4 square equal to 16. And 12 into 12 equal to 12 square equal to 144. In general, n into n equal to n square. Read as n raised to the power 2. Squares of first 20 natural numbers. Number, square. 1, 1. 2, 4. 3, 9. 4, 16. 5, 25. 6, 36. 7, 49. 8, 64. 9, 81. 10, 100. 11, 121, 12, 144, 13, 169, 14, 196, 15, 225, 16, 256, 17, 289, 18, 324, 19, 361, 20, 400. Interesting patterns involving square numbers. Numbers whose dot patterns can be arranged as triangles are known as triangular numbers. We see that 1, 3, 6, 10, 15 and so on can be arranged as triangles. So these are triangular numbers. Numbers whose dot patterns can be arranged as squares are known as square numbers. The numbers 4, 9, 16, 25 and so on are square numbers. Relationship between triangular numbers and square numbers. The sum of two consecutive triangular numbers is a square number. Let us understand this pattern with the following example. 1 plus 3 equal to 4 equal to 2 square. 3 plus 6 equal to 9 equal to 3 square. 6 plus 10 equal to 16 equal to 4 square. 10 plus 15 equal to 25 equal to 5 square. Numbers between consecutive square numbers. The pattern of square numbers helps us to find out the number of non-square numbers between two consecutive square numbers. Let us observe some examples of non-square numbers between two consecutive square numbers in the following table. Squares of consecutive natural numbers, non-square numbers between consecutive square numbers, number of non-square numbers between consecutive square numbers. 1 and 2, 1 square equal to 1, 2 square equal to 4. Between 1 and 4, 2, 3. 2 equal to 2 into 1. 2 and 3, 2 square equal to 4, 3 square equal to 9. Between 4 and 9, 5, 6, 7, 8. 4 equal to 2 into 2. 3 and 4, 3 square equal to 9. 4 square equal to 16. Between 9 and 16, 10, 11, 12, 13, 14, 15. 6 equal to 2 into 3. Up to n and n plus 1. N square, n plus 1 whole square. 2n equal to 2 into n. From the table, it is clear that the number of non-square numbers between the squares of two consecutive natural numbers n and n plus 1 is equal to 2n. This relationship is also linked with the difference in the consecutive square numbers. We can express the difference between two consecutive square numbers n square and n plus 1 whole square as n plus 1 whole square minus n square equal to n plus 1 plus n into n plus 1 minus n equal to 2n plus 1. Subtracting 1 from both the sides, we get n plus 1 whole square minus n square minus 1 equal to 2n. Therefore, the number of non-square numbers, that is 2n, between two consecutive square numbers n square and n plus 1 whole square is less than their difference. Perfect squares or square numbers. A natural number is called a perfect square or a square number if it is the square of a natural number. Some examples of perfect squares are 4 equal to 2 into 2, 9 equal to 3 into 3, 25 equal to 5 into 5, and 81 equal to 9 into 9. Here the numbers 4, 9, 25 and 81 are called perfect squares. Properties of perfect squares numbers. A number ending in 2, 3, 7 or 8 is never a perfect square. Example, 132, 143, 3267 and 1378 are not perfect squares as they have the digits 2, 3, 7 and 8 respectively in the ones place. The number of zeros at the end of a perfect square is always even. Example, 10,000 equal to 100 square, 2,500 equal to 50 square, 4,90,000 equal to 700 square. Square of an even number is always an even number. Example, 12 square equal to 144, 20 square equal to 400. Square of an odd number is always an odd number. Example, 9 square equal to 81, 17 square equal to 289. For any two consecutive natural numbers n and n plus 1, we have n plus 1 whole square minus n square equal to n plus 1 plus n into n plus 1 minus n equal to 2n plus 1. Example, 11 square minus 10 square equal to 11 plus 10 into 11 minus 10 equal to 2 into 10 plus 1 equal to 21. 15 square minus 14 square equal to 15 plus 14 into 15 minus 14 equal to 15 plus 2 into 14 plus 1 equal to 29. 35 square minus 34 square equal to 35 plus 34 into 35 minus 34 equal to 35 plus 34 equal to 2 into 34 plus 1 equal to 69. Pythagorean triplet. A triplet x, y, z of three natural numbers x, y and z is called Pythagorean triplet if x square plus y square equal to z square. Example, 6, 8, 10 is a Pythagorean triplet because 6 square plus 8 square equal to 36 plus 64 equal to 100 equal to 10 square. For any number m greater than 1, the Pythagorean triplet is given by 2m, m square minus 1, m square plus 1. Example, let us find the other two numbers of a Pythagorean triplet if one number of them is 12. We have for any natural number m, the Pythagorean triplet equal to 2m, m square minus 1, m square plus 1. Let m equal to 6, then 2m equal to 12. M square minus 1 equal to 6 square minus 1 equal to 36 minus 1 equal to 35. And m square plus 1 equal to 6 square plus 1 equal to 36 plus 1 equal to 37. Therefore, the other two numbers of the Pythagorean triplet are 35 and 37. The square of a natural number m is equal to the sum of the first m odd natural numbers. Example, 1 square equal to 1, sum of first 1 odd natural number. 2 square equal to 4 equal to 1 plus 3, sum of first 2 odd natural numbers. 3 square equal to 9 equal to 1 plus 3 plus 5, sum of first 3 odd natural numbers. And so on. In general, m square equal to 1 plus 3 plus 5 up to m terms, sum of first m odd natural numbers. Study the following patterns. Square of natural numbers other than the natural number 1 is either divisible by 3 or leaves a remainder 1 when divided by 3. Example, 2 square equal to 4 equal to 3 into 1 plus 1. 3 square equal to 9 equal to 3 into 3 plus 0. 4 square equal to 16 equal to 3 into 5 plus 1. 5 square equal to 25 equal to 3 into 8 plus 1. 6 square equal to 36 equal to 3 into 12 plus 0. Square of a natural number other than the natural number 1 is either divisible by 4 or leaves a remainder 1 when divided by 4. Example, 2 square equal to 4 equal to 4 into 1 plus 0. 3 square equal to 9 equal to 4 into 2 plus 1. 4 square equal to 16 equal to 4 into 4 plus 0. 5 square equal to 25 equal to 4 into 6 plus 1. 6 square equal to 36 equal to 4 into 9 plus 0. From the above, we can conclude that the square of numbers greater than 1 can be written as multiples of 3 or multiples of 3 plus 1. Square of numbers greater than 1 can also be written as multiples of 4 or multiples of 4 plus 1. Example 1. Using properties of perfect squares, check whether the following are perfect squares or not. A. 19. B. 36. Solution. A. 19 is neither a multiple of 3 nor 4. So 19 can never be a perfect square. B. 36 is divisible by 3 and 4 both. So 36 is a perfect square. Example 2. Find out the square of the following numbers using property of perfect square. A. 5 square. B. 7 square. Solution. From the property m square equal to sum of first m odd natural numbers. A. 5 square equal to 1 plus 3 plus 5 plus 7 plus 9 equal to 25. B. 7 square equal to 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 equal to 49. Example 3. Which of the following triplets are Pythagorean? A. 3, 4, 5. B. 1, 2, 3. Solution. A. We have 3 square plus 4 square equal to 9 plus 16 equal to 25 and 5 square equal to 25. Hence, 3 square plus 4 square equal to 5 square. Therefore, 3, 4, 5 is a Pythagorean triplet. B. We have 1 square plus 2 square equal to 1 plus 4 equal to 5 and 3 square equal to 9. Hence, 5 is not equal to 9. Therefore, 1, 2, 3 is not a Pythagorean triplet. Finding whether a given number is a perfect square or not. In order to check whether number is a perfect square or not, we follow the given steps. Write the number as the product of its prime factors. Group the prime factors into pairs. If all the factors can be paired, then the number is a perfect square. If the factors cannot be paired, the number is not a perfect square. Example 4. Find out the difference of the following squares. A. 44 square minus 43 square. B. 105 square minus 104 square. Solution. A. 44 square minus 43 square as n plus 1 whole square minus n square equal to 2n plus 1 equal to 2 into 43 plus 1 equal to 87. B. 105 square minus 104 square as n plus 1 whole square minus n square equal to 2n plus 1 equal to 2 into 104 plus 1 equal to 209. Example 5. Check whether the following are perfect squares or not. A. 144. Solution. A. Prime factorization of 144 equal to 2 into 2 into 2 into 2 into 3 into 3 as no factor is left after grouping the factors into pairs. So, 144 is a perfect square. Example 6. Find the smallest number by which 1008 should be multiplied to make it a perfect square. Solution. Prime factorization of 1008 equal to 2 into 2 into 2 into 2 into 3 into 3 into 7. Making pairs of the factors of 1008, we find that 7 does not have a pair. If 1008 is multiplied by 7, then all the factors of 1008 will become pairs and the number so obtained will be a perfect square. Therefore, the required smallest number is 7. Example 7. Find the smallest number by which 140 should be divided so that the quotient becomes a perfect square. Solution. 140 equal to 2 into 2 into 5 into 7. We notice that the prime factors 5 and 7 do not occur in pairs, so we eliminate them by dividing 140 by 35. That is 5 into 7. Therefore, the smallest number by which 140 should be divided so that the quotient becomes a perfect square is 35. Find the square of the following numbers. Find the sum without actual addition. Square roots. The square root of a number a is another number n, which when multiplied by itself gives a as the product. It means a equal to n into n equal to n square, or n is the square root of a. The statement states that n is the square root of a and can be expressed symbolically as under root a equal to n. Now observe the following examples. 4 equal to 2 square, where 2 is the square root of 4, that is, under root 4 equal to 2. 16 equal to 4 square, where 4 is the square root of 16, that is, under root 16 equal to 4. 49 equal to 7 square, where 7 is the square root of 49, that is, under root 49 equal to 7. All square numbers have both a positive square root and a negative square root. For example, both 5 into 5 and minus 5 into minus 5 are equal to 25. It means both plus 5 and minus 5 are the square roots of 25. That is, under root 25 equal to plus 5, minus 5 or plus minus 5. Note, a square root can be either negative or positive, but a negative number does not have a square root. In this chapter, when we refer to square root, we mean only the positive square root. Properties of square roots. Only perfect squares have the square roots as natural numbers. Negative numbers do not have square roots. Numbers ending in odd number of zeros do not have square roots as natural numbers. Numbers ending in 2, 3, 7, and 8 do not have square roots as natural numbers. Odd perfect squares have odd square roots and even perfect squares have even square roots. Methods of finding the square root of perfect squares. The square root of a perfect square may be found by any of the following two methods: prime factorization method, long division method. Prime factorization method. If the prime factors of any number a are a into b into b into c, then its square root is under root a equal to a into b into c. To find the square root of a perfect square by prime factorization method, we need to take the following steps. Step 1. Rewrite the given number as a product of prime factors. Step 2. Make pairs of the same factors. Step 3. Take a factor out of every pair of prime factors and find their product. Observe the following examples of square roots of perfect squares. Factors of perfect squares. Square roots. 16 equal to 2 into 2 into 2 into 2. Under root 16 equal to 2 into 2 equal to 4. 36 equal to 2 into 2 into 3 into 3. Under root 36 equal to 2 into 3 equal to 6. Example 8. Find the square root of 784 by prime factorization method. Solution. The prime factorization of 784 equal to 2 into 2 into 2 into 2 into 7 into 7. Hence, under root 784 equal to 2 into 2 into 7 equal to 28. Hence, under root 784 equal to 28. Long division method. The steps involved in the division method to find the square root of a number are explained below. Let's find the square root of the number 3,93,129. Step 1. Place a bar over every pair of digits starting from the ones digit. If the number of digits is odd, the leftmost bar will have only one digit. Step 2. Find the number whose square is equal to or less than the number formed by the first pair, that is 39, under the leftmost bar. In this case, 6 square is less than 39, which is less than 7 square. So we take 6 as the divisor and the number 39 as the dividend and get the remainder, that is 3. Step 3. Bring the number under the next bar, that is 31, to the right of the remainder to get the new dividend, that is 331. Step 4. Double the quotient and enter it with a blank on the right for the next digit of the next divisor. Step 5. Obtain the largest possible digit by trial and error method to fill the blank in the new divisor. The same digit, in this case 2, would also become the next digit in the quotient. Divide 331 with 122 and get the remainder. Step 6. Repeat the steps 3, 4 and 5 till all the pairs have been used. The final quotient, that is 627, will be the square root of the given number 3,93,129. Here, under root 3,93,129 equal to 627. Find the square root of the following numbers by prime factorization method. Finding the square root of rational numbers. The square root of a rational number can be found using the following property of perfect squares. If a and b are perfect squares, then under root a into b equal to under root a into under root b, and under root a upon b equal to under root a upon under root b. Example 14. Find the value of under root 25 into under root 64. Solution. Using property under root a into under root b equal to under root a into b, we have under root 25 into under root 64 equal to under root 25 into 64 equal to under root 5 into 5 into 2 into 2 into 2 into 2 into 2 into 2 equal to 5 into 2 into 2 into 2 equal to 40. Example 15. Find the square root of 121 upon 169. Solution: under root 121 upon 169 equal to under root 11 into 11 upon under root 13 into 13 equal to 11 upon 13. Example 16. Find the square root of 429 upon 49. Solution: under root 429 upon 49 equal to under root 225 upon 49 equal to under root 225 upon under root 49 equal to under root 15 into 15 upon under root 7 into 7 equal to 15 upon 7 equal to 2 1 upon 7. Finding the square root of decimal numbers. Depending on whether or not the given decimal number is a perfect square, we get an absolute or approximate square root as answer. Let us learn how to find the square root of a decimal number. Finding whether a given decimal number is a perfect square. Step 1. Place bars on the integral part of the decimal. Step 2. Also place bars on the decimal part starting from the first decimal place. If necessary, make the number of digits after decimal even by affixing a 0. Step 3. Start finding the square root of the entire decimal number by the long division process. Step 4. Place the decimal as soon as the integral part is used up in the division method. Step 5. Continue the division and stop when the remainder is 0. Example 17. Find the square root of 7.3441. Solution: under root 7.3441 equal to 2.71. When the decimal is not a perfect square, in this case, the procedure is the same as used for finding the square root of a perfect square decimal. The only difference in this case is that answer will be an approximate square root. Also, if we require the quotient corrected up to 2 decimal places, we affix zeros in the given number such that there are 3 pairs of numbers after the decimal. Finding the approximate square root without calculation. If the square root of a number is to be determined with a certain amount of approximation, we try to find 2 consecutive natural numbers between which the expected square root lies. Example 19. Find the square root of 247 to the nearest integer. Solution: 15 square equal to 225 and 16 square equal to 256. Since 225 is less than 247, which is less than 256, 15 is less than under root 247, which is less than 16. But 247 is closer to 256 than 225. So, under root 247 to the nearest integer equal to 16, or under root 247 equal to 16 approximately. Multiple choice questions. Chapter 4. Cubes and cube roots. Cubes. To find the cube of a number, just multiply it 3 times by itself. Can you tell what is 3 cubed? 3 cubed equal to 3 into 3 into 3 equal to 27. In general, if a number x is cubed, that is multiplied by itself 3 times, the number obtained is written as x cube, and we read it as x raised to the power 3. Therefore, if there exists a number c such that c equal to x cube, then c is called x cubed or the cube of x. Example, 2 cubed equal to 2 raised to the power 3 equal to 2 into 2 into 2 equal to 8. 8 is the cube of 2. 4 cubed equal to 4 raised to the power 3 equal to 4 into 4 into 4 equal to 64. 64 is the cube of 4. 5 cubed equal to 5 raised to the power 3 equal to 5 into 5 into 5 equal to 125. 125 is the cube of 5. 6 cubed equal to 6 raised to the power 3 equal to 6 into 6 into 6 equal to 216. 216 is the cube of 6. Finding whether a given number is a perfect cube or not. Step 1. Write the given numbers as the product of its prime factors. Step 2. Group together triples of the same prime factors. Step 3. If no factors are left out, the given number is a perfect cube. If any factor is left as a single factor or as a group of two factors, then the given number is not a perfect cube. For example, in the following, identify the number which are perfect cubes. A. 64, B. 243, C. 540. A. Resolving 64 into its prime factors. 64 equal to 2 into 2 into 2 into 2 into 2 into 2. As all factors of 64 can be grouped into triplets, so 64 is a perfect cube. B. Resolving 243 into its prime factors. 243 equal to 3 into 3 into 3 into 3 into 3. Here, after making the triplets of 3, we are left with 3 into 3. So 243 is not a perfect cube. C. Resolving 540 into its prime factors. 540 equal to 2 into 2 into 3 into 3 into 3 into 5. As since 2 into 2 and 5 are not forming triplets, so 540 is not a perfect cube. Properties of cubes of numbers. Cube of an even number is an even number. Example, 2 cube equal to 8, 4 cube equal to 64, 6 cube equal to 216, etc. Cube of an odd number is an odd number. Example, 3 cube equal to 27, 5 cube equal to 125, 7 cube equal to 343, etc. Cube of a negative number is negative. Example, minus 4 cube equal to minus 64, minus 5 cube equal to minus 125, minus 10 cube equal to minus 1000, etc. For any rational number p upon q, we have p upon q whole cube equal to p cube upon q cube, where q is not equal to 0. Example, what is the least natural number by which 2160 should be multiplied so that the product is a perfect cube? Solution, resolving 2160 into product of prime factors, we get 2160 equal to 2 into 2 into 2 into 2 into 3 into 3 into 3 into 5. Here 2 and 5 do not appear in the triplet. We need 2 into 2 into 5 into 5 to make their triplet so that the number becomes a perfect cube. Hence, 2 into 2 into 5 into 5 equal to 100. Example, by which smallest number should minus 250 be divided so that the quotient becomes a perfect cube? Solution. Minus 250 equal to minus 1 into 250 equal to minus 1 into 5 into 5 into 5 into 2. We observe that making group of 3, 2 is left alone. So to make minus 250 a perfect cube, we should divide by 2. Methods of finding the cube roots by successive subtraction. The cubes of natural numbers have interesting patterns. 2 cube equal to 8. 2 cube minus 1 cube equal to 7. Equal to 1 plus 1 into 6. Equal to 1 plus 2 into 1 into 3. 3 cube equal to 27. 3 cube minus 2 cube equal to 19. Equal to 1 plus 1 into 6 plus 2 into 6 equal to 1 plus 3 into 2 into 3. 4 cube equal to 64. 4 cube minus 3 cube equal to 37 equal to 1 plus 1 into 6 plus 2 into 6 plus 3 into 6 equal to 1 plus 4 into 3 into 3. 5 cube equal to 125. 5 cube minus 4 cube equal to 61 equal to 1 plus 1 into 6 plus 2 into 6 plus 3 into 6 plus 4 into 6 equal to 1 plus 5 into 4 into 3. 9 cube equal to 729. 9 cube minus 8 cube equal to 217 equal to 1 plus 1 into 6 plus 2 into 6 plus up to 8 into 6 equal to 1 plus 9 into 8 into 3. From the above patterns we have 1 equal to 1 cube, 1 plus 7 equal to 2 cube, 1 plus 7 plus 19 equal to 3 cube, 1 plus 7 plus 19 plus 37 equal to 4 cube, 1 plus 7 plus 19 plus 37 plus 61 equal to 5 cube. 1 plus 7 plus 19 plus 37 plus 61 up to plus 217 equal to 9 cube. Therefore, considering the numbers 1, 7, 19, 37 up to 217, we notice that 2 cube is the sum of the first two numbers, that is 1, 7. 3 cube is the sum of the first three numbers, that is 1, 7, 19. 9 cube is the sum of the first 9 numbers, that is 1, 7, 19, 37 up to 217. To find the cube root of a given number, we successively subtract the numbers 1, 7, 19, 27, 61 and so on from the given number till we get 0. The number of subtractions required to get 0 is the cube root of the given number. Example: find the cube root of 125. Solution: using the successive subtraction method, we get 125 minus 1 equal to 124. 124 minus 7 equal to 117. 117 minus 19 equal to 98. 98 minus 37 equal to 61. 61 minus 61 equal to 0. Since we have subtracted 5 times to get 0, therefore the cube root of 125 is 5. By prime factorization, this method involves the following steps. Step 1. Resolve the given number into product of prime factors. Step 2. Group the same factors in triplets. Step 3. Take one factor from each group of triplets formed in Step 2. Step 4. Find the product of all the factors obtained in Step 3. This product is the cube root of the given number. Example 5. Find the cube root of 9261 by prime factorization method. Solution: 9261 equal to 3 into 3 into 3 into 7 into 7 into 7. Therefore, cube root of 9261 equal to 3 into 7 equal to 21. Cube roots of negative numbers. We know that for a positive integer m, perfect cube, minus m is a negative integer such that minus m equal to minus 1 into m. Therefore, cube root of minus m equal to cube root of minus 1 into cube root of m. Cube root of minus m equal to minus 1 into n, where n is the cube root of the perfect cube m. Hence, cube root of minus m equal to minus n. Hence, if m is a perfect cube whose cube root is n, then the cube root of minus m is minus n. Example. Find the cube root of minus 1331. Solution. Cube root of minus 1331 equal to cube root of minus 11 into minus 11 into minus 11 equal to minus 11. Cube roots of rational numbers. For finding the cube root of a rational number, we use the following property. Cube root of a upon b equal to cube root of a upon cube root of b. Let us find the cube root of 343 upon 729. Resolving 343 and 729 into prime factors, we get 343 equal to 7 into 7 into 7. 729 equal to 9 into 9 into 9. We have cube root of 343 equal to 7 and cube root of 729 equal to 9. Therefore, cube root of 343 upon 729 equal to 7 upon 9. Example. Find the cube root of the following by prime factorization method. A. 729. Solution. A. Cube root of 729 equal to cube root of 3 into 3 into 3 into 3 into 3 into 3 equal to 3 into 3 equal to 9. Example. Find the cube root of 1331 upon 9261. Solution. Cube root of 1331 upon 9261 equal to cube root of 1331 upon cube root of 9261 equal to cube root of 11 into 11 into 11 upon cube root of 3 into 3 into 3 into 7 into 7 into 7 equal to 11 upon 3 into 7 equal to 11 upon 21. Find the cube roots of the following numbers by successive subtraction. Find the cube roots of the following by prime factorization method. Find the cube roots of the following. Find the cube roots of the following. Multiple choice questions. Chapter 5. Playing with numbers. Generalized form of numbers. A number is said to be in generalized form or expanded form if it is expressed as the sum of the product of its digits with their respective place values. For example, a two-digit number, say 34, can be written in the expanded form as 34 equal to 30 plus 4. And a three-digit number, say 728, can be written in the expanded form as 728 equal to 700 plus 20 plus 8. In general, if we consider any two-digit number as AB, where A and B are digits, then we have AB equal to 10A plus B and BA equal to 10B plus A, where BA is the number obtained by interchanging the digits. And if ABC is a three-digit number, where A, B and C are digits, then we have ABC equal to 100A plus 10B plus C, BCA equal to 100B plus 10C plus A, and CAB equal to 100C plus 10A plus B. Example, write the following numbers in generalized form. A. 32, B. 78, C. 168. Solution A. 32 equal to 3 into 10 plus 2. B. 78 equal to 7 into 10 plus 8. C. 168 equal to 1 into 100 plus 6 into 10 plus 8. Example, write the following numbers in usual form. A. 20 into 5 plus 6. B. 100 plus 80 plus 7. C. 100 into 7 plus 10 into 1 plus 3. Solution A. 20 into 5 plus 6 equal to 100 plus 6 equal to 106. B. 100 plus 80 plus 7 equal to 187. C. 100 into 7 plus 10 into 1 plus 3 equal to 700 plus 10 plus 3 equal to 713. Write the following numbers in generalized form. Divisibility rules. In the previous classes, we have learned how to test a number for its divisibility by other numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Now let us learn about some divisibility rules that are based on the generalized form of a number. The test of divisibility by number A is a shortcut method of finding whether a given number B is divisible by the number A or not. Divisibility rule for 10. Take any number which may have any number of digits. If A is the ones digit of the number, B is its tenth digit, and C is its hundredth digit, and so on, then its generalized form will be 100C plus 10B plus A, which can be written in the form of 10K plus A, where K is equal to B plus 10C. It is obvious that since 10K is a multiple of 10, the number 10K plus A will also be a multiple of 10 if A is 0. So, the divisibility rule for 10 is that a number is divisible by 10 if and only if its ones digit is 0. Divisibility rule for 5. We have just seen that any number can be written as 10K plus A. Any number that is a multiple of 10 is also a multiple of 5. It implies that 10K is also a multiple of 5. Now the number 10K plus A will be divisible by 5 if A is divisible by 5, and A will be divisible by 5 only if A is either 0 or 5. So, divisibility rule for 5 is that a number is divisible by 5 if and only if its ones digit is 0 or 5. Divisibility rule for 2. A number can be written in the form of 10K plus A, and 10K is a multiple of 2. It follows that the number 10K plus A will be divisible by 2 if and only if A is divisible by 2, and A will be divisible by 2 if it is an even number. That is, A is either 0, 2, 4, 6 or 8. So the divisibility rule for 2 is that a number is divisible by 2 if its ones digit is 0, 2, 4, 6 or 8. Divisibility rule for 9. When a number is written in the form of 10k plus a, it is easy to decide its divisibility by 2, 5, 10 only on the basis of the divisibility of its ones digit a by 2, 5 or 10, since 10k is divisible by 2, 5 and 10. But this conclusion will not help us in deciding the divisibility of a number by 3 or 9, since 10k need not always be a multiple of 3 and 9. So to find the divisibility rules for 9, we rewrite the generalized form of the number as plus 1000d plus 100c plus 10b plus a equal to plus 999 plus 1 into d plus 99 plus 1 into c plus 9 plus 1 into b plus a equal to plus 999d plus 99c plus 9b plus bracket plus d plus c plus b plus a equal to 9 into bracket plus 111d plus 11c plus 1b plus bracket plus d plus c plus b plus a equal to 9 into k plus bracket plus d plus c plus b plus a. For any given number, since 9k will be divisible by 9, the number itself will be divisible by 9 if and only if bracket plus d plus c plus b plus a, or the sum of the digits of the number is divisible by 9. So the divisibility rule for 9 is that a number is divisible by 9 if the sum of its digit is divisible by 9. Divisibility rule for 3. In the case of divisibility rule for 9, the number is written as 9 into k plus bracket plus d plus c plus b plus a. Since 9k is divisible by 3, the number will be divisible by 3 if and only if bracket plus d plus c plus b plus a, or the sum of the digits of the number is divisible by 3. So the divisibility rule for 3 is that number is divisible by 3 if the sum of its digits is divisible by 3. Remember, if a number is divisible by 9, it is divisible by 3 also, but the converse is not true. Find out which of these numbers are divisible by 2 and 5, which by 10. Number puzzles and games. Cryptarithmus. Cryptarithmus are mathematical puzzles in which symbols or letters of English alphabet are used to represent certain digits. And we have to find out which letter represents which digit. The rules followed in Cryptarithmus are: a letter used in the puzzle can represent only one digit. Similarly, one digit is represented by only one letter. This means that in a given puzzle, if the letter A represents the digit 5, A cannot be used to represent any other digit in that puzzle. And the digit 5 cannot be represented by any other letter in the same puzzle. The first digit of a number cannot be 0. For example, the number 47 is written as 47 only. It cannot be written as 047 or 0047. Magic square. Look at the given square. In a magic square, each row, column and diagonal add up to the same number. Let us solve this magic square given that each row, column and diagonal add up to 111. Since each row adds up to 111, so the missing number in the first row must be 111 minus 67 plus 1 equal to 43. Similarly, find the numbers for other rows, columns and diagonals. The final grid will look like. Example, find the values of the letters used in the following puzzle. Solution, consider the digit in the ones place. We have 8 plus a equal to 1, a equal to 3. Substituting a equal to 3, we get 8 plus 3 equal to 11, which gives us 1 in the ones place. Now the puzzle reduces to, here again we have 1 plus 6 plus b equal to 6. Hence, 7 plus b equal to 6. Again, b is a digit and it can be equal to 9. Since 9 plus 7 equal to 16, which gives 6 in the tens place. Substituting b equal to 9, we get. Total comes 961. Multiple choice questions. Fill in the blanks. Chapter 6. Algebraic Expressions. Algebraic Expressions. An algebraic expression is a combination of constants and variables connected by the signs of fundamental operations, that is, plus, minus, multiply or division. Example, 3x plus 5y minus 7z, 3abc minus 4b, and 6x square plus 5 etc. are algebraic expressions. Variables and constants. A quantity which takes different numerical values in different expressions is called a variable or literal, and a quantity which has a fixed numerical value is called a constant. Example, in 3x square plus 5y minus 7, 3, 5, 7 are constants and x and y are variables. Terms. Different parts of an algebraic expression connected by plus and minus sign are called terms. Example, 7a square plus 5b minus 2abc is an algebraic expression, where 7a square, 5b and minus 2abc are three different terms. Coefficient. Any factor of a non-constant term of an algebraic expression is called the coefficient of the remaining factors of the term. In particular, the constant part is called the numerical coefficient, or simply the coefficient of the term, and the remaining part is called the literal coefficient of the term. Example, consider the expression 7p square q cube minus 5pq square minus 3p plus 2. In the term 7p square q cube, the numerical coefficient equal to 7 and the literal coefficient equal to p square q cube. Like and unlike terms. Terms of an algebraic expression are said to be like terms if they have the same variable. The variable must also have the same power in the terms. However, the coefficients of the variable may be different. Terms either not having the same variable or those with the same variable but unequal powers are called unlike terms. The following table shows some examples of like and unlike terms. Like terms. Unlike terms. Like terms. 8a, 14a, minus 6a, 20a, minus 13a. PQR, 49QPR, 8RPQ, minus 3PQR. Unlike terms. 14a, 14b, 14c, 14x, 14y, 7a cube, a square, a, 6 a raised to the power 0. Factors. A term of an algebraic expression can be written as a product of one or more numbers and variables. These numbers and variables are called the factors of that term. Example, the term 5xy is the product of its factors 5x and y. Here 5 is the numerical factor, while x and y are literal factors. Types of algebraic expression. Monomials, binomials, and trinomials. An algebraic expression is said to be a monomial if it contains only one term. Example, 4xy, 12abc, 8axby, minus 7xyz, 5a square b square are monomials. An algebraic expression is said to be a binomial if it contains two unlike terms. Example, ax plus b, 11a plus 7b, 9pq minus r, 14m square plus 8 are binomials. An algebraic expression is said to be a trinomial if it contains three unlike terms. Example, 2x plus 3y plus 4z, 4ab plus 7cd plus 9, 2p square plus 5q square plus r square are trinomials. Polynomial. An algebraic expression is said to be a polynomial if there is one or more than one term in the expression. There are variables with non-negative integral exponents in the expression. Example, minus 7x square minus 4x plus 5, x raised to the power 4 minus 2x square plus 12x plus 7, a square plus b square plus c square are polynomials. Degree of a polynomial. In case of polynomials of one variable, it is the highest power of the variable. Example, the degree of expression 5x raised to the power 4 plus 3x cube minus 2x square minus 7 is 4. Since the highest power of the variable is 4, the degree of expression 3z square minus 2z plus 11 is 2. Since the highest power of the variable is 2. In case of polynomials with two or more than two variables, we first find the sum of the exponents of the variables in each term. The highest value among these sums is the degree of the polynomial. Example, in algebraic expression 3xy square plus 4xy plus 5y, first term 3xy square, sum of the exponent equal to 1 plus 2 equal to 3. Second term 4xy, sum of exponent equal to 1 plus 1 equal to 2. Third term 5y, sum of exponent equal to 1. The highest value among the above terms is 3. So the degree of the polynomial is 3. Addition and subtraction of algebraic expressions. For addition and subtraction of two or more than two algebraic expressions, we first collect like terms and then find the sum or difference of the coefficients of these terms. Example, add x cube minus 2x square y plus 5xy, 2x cube plus 5xy, and minus 5x square y minus 3x cube plus 7xy. Solution, x cube minus 2x square y plus 5xy plus 2x cube plus 5xy plus minus 5x square y minus 3x cube plus 7xy equal to x cube minus 2x square y plus 5xy plus 2x cube plus 5xy minus 5x square y minus 3x cube plus 7xy. equal to x cube plus 2x cube minus 3x cube minus 2x square y minus 5x square y plus 5xy plus 5xy plus 7xy equal to minus 7x square y plus 17xy. Example, subtract 2x square y plus 5xy square minus 3y cube from y cube minus 3x square y. Solution, y cube minus 3x square y minus bracket 2x square y plus 5xy square minus 3y cube equal to y cube minus 3x square y minus 2x square y minus 5xy square plus 3y cube equal to y cube plus 3y cube minus 3x square y minus 2x square y minus 5xy square equal to 4y cube minus 5x square y minus 5xy square. Addition and subtraction of algebraic expressions. For addition and subtraction of two or more than two algebraic expressions, we first collect multiplication of algebraic expressions. Before going through the multiplication of algebraic expressions, we must remember the following points. The product of two factors with like signs is positive, and the product of two factors with unlike signs is negative. That is, plus into plus equal to plus, plus into minus equal to minus, minus into plus equal to minus, and minus into minus equal to plus. If x is any variable and m and n are positive integers, then x raised to the power m into x raised to the power n equal to x raised to the power m plus n, and x raised to the power m wholes raised to the power n equal to x raised to the power mn. Multiplication of a monomial by a monomial. Consider 4x cube into 5x square. We know 4x cube equal to 4 into x into x into x, and 5x square equal to 5 into x into x. 4x cube into 5x square equal to 4 into x into x into x into 5 into x into x equal to 4 into 5 into x into x into x into x into x equal to 20 into x raised to the power 5 equal to 20x raised to the power 5. Above multiplication can be performed by using following three steps. Multiply the numerical coefficients of both the monomials, multiply the variables, multiply the above two results. Multiplication of more than two monomials. The following rule can be used for multiplying any number of monomials. The coefficient of the product of the given monomials is the product of the coefficients of these monomials. The exponent of each literal is the sum of the exponents of this literal in the given monomials. Example, find the product of a minus 5a square b square and a square b square, b minus 4 upon 3 x square y and 2y square x square. Solution, a minus 5a square b square into a square b square equal to minus 5 into 1 into a square b square into a square b square equal to minus 5 into a raised to the power 2 plus 2 into b raised to the power 2 plus 2 equal to minus 5 into a raised to the power 4 into b raised to the power 4 equal to minus 5 a raised to the power 4 b raised to the power 4. B. Minus 4 upon 3 x square y into 2y square x square equal to minus 4 upon 3 into 2 into x square into y square equal to minus 8 upon 3 into x raised to the power 2 plus 2 into y raised to the power 1 plus 2 equal to minus 8 upon 3 x raised to the power 4 y cube. Example. Find the product of a 5p square q square into minus 7 pq into minus 8 p cube q square. B. Minus 3x square y into 4xy square into 6x square yz. Solution. A. 5p square q square into minus 7 pq into minus 8 p cube q square equal to 5 into minus 7 into minus 8 into p square into p cube into q square into q square equal to 280 into p raised to the power 2 plus 1 plus 3 into q raised to the power 2 plus 1 plus 2 equal to 280 p raised to the power 6 q raised to the power 5. B. Minus 3x square y into 4xy square into 6x square yz equal to minus 3 into 4 into 6 into x square into x square into y square into y into z equal to minus 72 into x raised to the power 2 plus 1 plus 2 into y raised to the power 1 plus 2 plus 1 into z equal to minus 72 into x raised to the power 5 into y raised to the power 4 into z equal to minus 72 x raised to the power 5 y raised to the power 4 z. Multiplication of a binomial by a monomial. To multiply a binomial by a monomial, we multiply every term of the binomial by the monomial and then add the products. In other words, we use the distributive property according to which if a, b, c are any three rational numbers, then a into b plus c equal to a into b plus a into c and a into b minus c equal to a into b minus a into c. Example. A 6x square y into x plus 2y equal to 6x square y into x plus 6x square y into 2y equal to 6x cube y plus 6 into 2 into x square y into y equal to 6x cube y plus 12x square y square. B. 2pq into 6pq minus 11qr equal to 2pq into 6pq plus 2pq into minus 11qr equal to 2 into 6 into pq plus 2 into minus 11 into pq into qr equal to 12p square q square minus 28pq square r. Multiplication of two binomials. To multiply a binomial by another binomial, we multiply every term of one binomial by every term of the other binomial and add the products, and also combine like terms if any. Example. Multiply 7a plus 11b by 13a plus 9b. Solution. 7a plus 11b into 13a plus 9b equal to 7a into 13a plus 9b plus 11b into 13a plus 9b equal to 7a into 13a plus 7a into 9b plus 11b into 13a plus 11b into 9b equal to 91a square plus 63ab plus 143ab plus 99b square equal to 91a square plus 206ab plus 99b square. This multiplication can also be performed by column method as follows. Let a, b, c and d are four monomials. Then a plus b into c plus d equal to ad plus bd. Multiply a plus b by d. ac plus bc. Multiply a plus b by c equal to ac plus bc plus ad plus bd. Multiplication of a binomial and a trinomial. Multiplication of a binomial and a trinomial can be performed using distributive property of multiplication over addition. If a, b, c, d and e are five monomials, then a plus b into c plus d plus e equal to a into c plus d plus e plus b into c plus d plus e equal to ac plus ad plus ae plus bc plus bd plus be. Example. Find the products a minus 8y into 2xy plus 3y square, b 5a into 8a plus 9b. Solution. A minus 8y into 2xy plus 3y square equal to minus 8y into 2xy plus minus 8y into 3y square equal to minus 16xy square minus 24y cube. B 5a into 8a plus 9b equal to 5a into 8a plus 5a into 9b equal to 40a square plus 45ab. Example. Multiply 11p minus 9q by 4p plus 17q. Solution. 11p minus 9q into 4p plus 17q equal to 11p into 4p plus 17q plus minus 9q into 4p plus 17q equal to 11p into 4p plus 11p into 17p minus 9q into 4p minus 9q into 17q equal to 44p square plus 187pq minus 36pq minus 153q square equal to 44p square plus 151pq minus 153q square. Example. Multiply 2x square minus 3x plus 5 by 5x plus 2. Solution. 5x plus 2 into 2x square minus 3x plus 5 equal to 5x into 2x square minus 3x plus 5 plus 2 into 2x square minus 3x plus 5 equal to 5x into 2x square plus 5x into minus 3x plus 5x into 5 plus 2 into 2x square plus 2 into minus 3x plus 2 into 5 equal to 10x cube minus 15x square plus 25x plus 4x square minus 6x plus 10 equal to 10x cube minus 15x square plus 25x plus 4x square minus 6x plus 10 equal to 10x cube minus 15x square plus 4x square plus 25x minus 6x plus 10 equal to 10x cube minus 11x square plus 19x plus 10. Division of algebraic expressions. Division of a monomial by a monomial. The division of a monomial by a monomial is alike to the division of integers. Let A and B are two monomials, then A divided by B equal to C, or A upon B equal to C, where C is the quotient, A is the dividend, and B is the divisor. Example: divide A, 24A raised to the power 4 divided by 6A. Solution: A, 24A raised to the power 4 divided by 6A equal to 24A raised to the power 4 upon 6A equal to 24 upon 6 into A into A into A into A upon A equal to 4A cube. Division of a polynomial by a monomial. For dividing a polynomial by a monomial, we divide each term of the polynomial by the monomial. Example: divide 24a cube b cube plus 18a square b square plus 12ab by 6ab. Solution: we have 24a cube b cube plus 18a square b square plus 12ab divided by 6ab equal to 24a cube b cube upon 6ab plus 18a square b square upon 6ab plus 12ab upon 6ab equal to 4a square b square plus 3ab plus 2. Division of a polynomial by a binomial or a polynomial by long division method. For dividing a polynomial by long division method, we follow the given steps. Arrange the terms of the dividend and the divisor in descending order of their degrees. Divide the first term of the dividend by the first term of the divisor to obtain the first term of the quotient. Multiply the divisor by the first term of the quotient and subtract the result from the dividend to obtain the remainder. Consider the remainder, if any, as dividend and repeat step 2 to obtain the second term of the quotient. Repeat the above process till we obtain a remainder which is either 0 or a polynomial of degree less than that of the divisor. Example: divide x cube minus 6x square plus x plus 8 by x plus 1. Solution: explanation: divide x cube by x. X cube divided by x equal to x square. Now multiply each term of x plus 1 by x square and write the product below the dividend at their proper place. On subtracting, x cube get cancelled and minus 6x square minus x square equal to minus 7x square will remain. Divide minus 7x square by x, that is, minus 7x square divided by x equal to minus 7x, the second term of the quotient. Again multiply x plus 1 by minus 7x and subtract. 7x square will be cancelled and x plus 7x equal to 8x will remain. Again, 8x divided by x equal to 8 is the third quotient. Multiply x plus 1 by 8 to obtain 8x plus 8. On subtraction, the remainder is 0. Hence, the quotient is x square minus 7x plus 8. Let us understand with another example. Example: divide 5x cube minus 4x square plus 3x plus 24 by 5x plus 6. Solution: hence, the quotient is x square minus 2x plus 3 and the remainder is 6. Algebraic identities. We have already learned about the concept of simple equations in previous classes. Do you know what is the difference between an equation and an identity? The following examples will help you understand this difference. Consider the equation 5x plus 6 equal to 16. For x equal to 2, LHS equal to 5 into 2 plus 6 equal to 16, RHS equal to 16. No other value of x will balance the above equation. Try putting x equal to minus 2. LHS equal to 5 into minus 2 plus 6 equal to minus 10 plus 6 equal to minus 4. RHS equal to 16. Thus, for x equal to minus 2, LHS is not equal to RHS. So the equation 5x plus 6 equal to 16 is true only for x equal to 2. Whereas an identity is an equation which is true for all values of its variables. Consider the equation p plus 2 into p plus 3 equal to p square plus 5p plus 6. Let us evaluate the above equation for different values of p. 1. Let p equal to 3, LHS equal to p plus 2 into p plus 3 equal to 3 plus 2 into 3 plus 3 equal to 5 into 6 equal to 30. RHS equal to 3 square plus 5 into 3 plus 6 equal to 9 plus 15 plus 6 equal to 30. LHS equal to RHS. 2. Let p equal to minus 4, LHS equal to minus 4 plus 2 into minus 4 plus 3 equal to minus 2 into minus 1 equal to 2. RHS equal to minus 4 square plus 5 into minus 4 plus 6 equal to 16 minus 20 plus 6 equal to 2. LHS equal to RHS. We find that for all values of p, LHS equal to RHS. Thus, an equation that is true for every value of its variables is called an identity. Therefore, p plus 2 into p plus 3 equal to p square plus 5p plus 6 represents an identity. Standard identities. The identities which are obtained by multiplying one binomial with another binomial are called standard identities. Let us study some standard identities. A plus b whole square equal to a square plus 2ab plus b square. Proof. A plus b whole square equal to a plus b into a plus b equal to a into a plus b plus b into a plus b equal to a square plus ab plus ba plus b square equal to a square plus 2ab plus b square, since ab equal to ba. Therefore, a plus b whole square equal to a square plus 2ab plus b square. It can be verified that the above identity is true for all values of its variables a and b. A minus b whole square equal to a square minus 2ab plus b square. Proof. A minus b whole square equal to a minus b into a minus b equal to a into a minus b into a minus b equal to a square minus ab minus ba plus b square equal to a square minus 2ab plus b square, since ab equal to ba. Therefore, a minus b whole square equal to a square minus 2ab plus b square. A plus b into a minus b equal to a square minus b square. Proof. A plus b into a minus b equal to a into a minus b plus b into a minus b equal to a square minus ab plus ba minus b square, since ab equal to ba equal to a square minus b square. Therefore, a plus b into a minus b equal to a square minus b square. Example. Find the following products. A. 5x plus 6y into 5x plus 6y. B. 3a minus 2b into 3a minus 2b. Solution A. We have 5x plus 6y into 5x plus 6y equal to 5x plus 6y whole square equal to 5x whole square plus 2 into 5x into 6y plus 6y square using a plus b whole square equal to a square plus 2ab plus b square equal to 25x square plus 60xy plus 36y square. B. 3a minus 2b into 3a minus 2b equal to 3a minus 2b whole square equal to 3a square minus 2 into 3a into 2b plus 2b square using a minus b whole square equal to a square minus 2ab plus b square equal to 9a square minus 12ab plus 4b square. Example. Find the continued product using the identities a plus b into a minus b into a square plus b square. Solution. A plus b into a minus b into a square plus b square equal to a square minus b square into a square plus b square. Using a plus b into a minus b equal to a square minus b square equal to a square whole square minus b square whole square equal to a raised to the power 4 minus b raised to the power 4. Using identity, evaluate the following. Find the value of x if multiple choice questions, Chapter 7 Factorization. Factorization of algebraic expressions. When an algebraic expression is written as the product of two or more expressions, then each of these expressions are called factors of the given expression. Example, in the algebraic expression 2xy plus 5y, the term 2xy is formed by the product of 2, x and y. So we can say that 2x and y are the factors of 2x, y. Let us consider some more examples. 6x into 3y equal to 18xy. A plus b into a minus b equal to a square minus b square. In the above examples, 6x and 3y are the factors of the product 18xy, and a plus b, a minus b are the factors of the product a square minus b square. Let us find all the possible factors of 6b. 6b equal to 1 into 6b equal to 6 into b equal to 2 into 3b equal to 2 into 3 into b. Therefore, all possible factors of 6b are 1, 2, 3, 6b, 3b, 6b. Example. Find all possible factors of 5a square b. Solution. 5a square b equal to 1 into 5a square b equal to 5 into a square b equal to 5a into ab equal to 5ab into a equal to a square into 5b equal to b into 5a square. Thus, all possible factors of 5a square b are 1. 5a square b, 5a square b, 5a, ab, 5ab, a square, 5b, b, 5a square. Common factors of monomials. Let us consider the monomials 3a square b and 11ab square. All the possible factors of 3a square b are 3 into a square b, 3a into ab, a square into 3b, b into 3a square, 1 into 3a square b, 3ab into a, 3 into a square into b. All the possible factors of 11ab square are 11 into ab square, 11a into b square, a into 11b square, b into 11ab, 1 into 11ab square, 11b into ab, 11 into a into b square. Thus, 3a square b equal to 1, 3b, 3a, a square, 3a square, b, 3b, ab, 3ab, a square b, 3a square b, and 11ab square equal to 1, 11, a, 11a, b, 11b, b square, 11b square, ab, 11ab, ab square, 11ab square. The factors a, b, ab are common to both 3a square b and 11ab square. Thus, they are called the common factors of 3a square b and 11ab square. Remember, 1 is a factor of every algebraic term and it is called a trivial factor. Highest common factor, greatest common factor of monomials. HCF of two or more monomials equal to HCF of their numerical coefficient into HCF of their literal coefficients. HCF of literal coefficients equal to product of each common literal raised to the lowest power. The highest common factor, HCF of two or more monomials, can be determined as follows. Determine the HCF of the numerical coefficients of the given monomials. Take out the common variables with least power. Product of the HCF of the numerical coefficients and the common variables with the least power will be the HCF of the given monomials. Example, find the HCF of 6x square and 30xy square. Solution, HCF of 6 and 30 is 6. HCF of x square and xy square is x. Hence, the HCF of 6x square and 30xy square equal to 6x. Factorization when a common monomial factor occurs in each term. In this case, the given expression is expressed as a product of the greatest common monomial and the quotient obtained by dividing the given expression by this greatest common monomial. Example, factorize the following: a 21a square b plus 35ab square, b 9pq plus 15qr, c 5x square plus 9x. Solution, a 21a square b plus 35ab square equal to 7ab into 3a plus 5b, b 9pq plus 15qr equal to 3q into 3b plus 5r, c 5x square plus 9x equal to x into 5x plus 9. Factorization when a binomial is common. In this case, the given expression is expressed as the product of the common binomial and the quotient obtained by dividing the given expression by this common binomial. Example, factorize the following: a 5 into 3x plus 2y whole cube minus 10 into 3x plus 2y whole square, b x square into y plus 2 plus 9 into y plus 2. Solution, a 5 into 3x plus 2y whole cube minus 10 into 3x plus 2y whole square equal to 5 into 3x plus 2y whole square into 3x plus 2y minus 2 equal to 5 into 3x plus 2y whole square into 3x plus 2y minus 2. b x square into y plus 2 plus 9 into y plus 2 equal to y plus 2 into x square plus 9. Factorization by regrouping the terms. Sometimes it is not possible to take out a common factor from all the terms of the given expression. In that case, we factorize the expression in the following manner. Arrange the terms of the given expression in groups in such a way that each group has the same common factor. Factorize each group. Take out the factor which is common to each group. This method of factorization is known as factorization by grouping the terms. Example: factorize a x square plus ax plus bx plus ab. b 12ax minus 4ab plus 18bx minus 6b square. Solution: a x square plus ax plus bx plus ab equal to x square plus bx plus ax plus ab equal to x into x plus b plus a into x plus b equal to x plus a into x plus b. b 12ax minus 4ab plus 18bx minus 6b square equal to 12ax plus 18bx minus 4ab plus 6b square equal to 3x into 4a plus 6b minus b into 4a plus 6b equal to 4a plus 6b into 3x minus b equal to 2 into 2a plus 3b into 3x minus b. Find the greatest common factor of the following monomials. Factorization using algebraic identities. Factorization when a binomial is the difference of two squares. In this case, we use the following identity: x square minus y square equal to x plus y into x minus y. Example: factorize the following: a 16x square minus 81y square, b 4x square y square minus 25y square. Solution: a 16x square minus 81y square equal to 4x whole square minus 9y whole square, as x square minus y square equal to x plus y into x minus y equal to 4x plus 9y into 4x minus 9y. b 4x square y square minus 25y square equal to 2xy whole square minus 5y whole square, as x square minus y square equal to x plus y into x minus y equal to 2xy plus 5y into 2xy minus 5y. Factorization when an expression is a perfect square. In this case, we use the following identities: x square plus 2xy plus y square equal to x plus y whole square equal to x plus y into x plus y. X square minus 2xy plus y square equal to x minus y whole square equal to x minus y into x minus y. Example: factorize a 9x square plus 24x plus 16, b 4x square y square minus 4xyz plus z square. Solution: a 9x square plus 24x plus 16 equal to 3x whole square plus 2 into 3x into 4 plus 4 square, as x plus y whole square equal to x square plus 2xy plus y square equal to 3x plus 4 whole square. b 4x square y square minus 4xyz plus z square equal to 2xy whole square minus 2 into 2xy into z plus z square, as x minus y whole square equal to x square minus 2xy plus y square equal to 2xy minus z whole square. Factorization by splitting the middle term. Expressions like px square plus qx plus r or px square plus qxy plus ry square are neither a square nor in the form of x plus a into x plus b equal to x square plus a plus b into x plus ab. Such expressions are factorized by splitting their middle terms. For example, the middle term qx of the expression px square plus qx plus r is split into two terms as ax and bx, such that their sum is qx and their product is equal to the product of the first and the third term. Example, factorize a x square minus 9x plus 20, b x square minus 2x minus 24. Solution a x square minus 9x plus 20 equal to x square minus 5x plus 4x plus 20. X square minus 5x minus 4x plus 20 equal to x into x minus 5 minus 4 into x minus 5. Split 9 into two parts such that their sum is 9 and product is 20 equal to x minus 5 into x minus 4. B x square minus 2x minus 24 equal to x square minus 6x minus 4x minus 24. Now equal to x square minus 6x plus 4x minus 24. Split 2 into two parts such that their difference is 2 and product is 24 equal to x into x minus 6 plus 4 into x minus 6 equal to x minus 6 into x plus 4. Multiple choice questions. Chapter 8. Linear equations in one variable. Linear equations in one variable. A linear equation in one variable is an equation in which the highest exponent or power of the variable is 1. The following equations are linear equations in one variable with variables x, y, and m respectively. 2x minus 7 equal to 21, 5y equal to 125, 3m minus 2 equal to 83. One way of describing an equation is in terms of its degree. The degree of an equation is equal to the highest power of the variable in it. If an equation has only one variable and the highest power of the variable is 1, then it is called a linear equation in one variable. In the above equations, the power of x, y, and m are 1. So they represent linear equations. Features of an equation. While working with equations, keep the following points in mind: RHS and LHS. In an equation, the expression on the left of equality sign is called the left-hand side, LHS, and the expression on the right of equality sign is called the right-hand side, RHS. Example, equality sign, 3x plus 5, LHS, 11 RHS. Solution of an equation. In an equation, we can substitute different values for the variable, but the values of the LHS and RHS expressions will be equal only for certain values of the variable. For example, the equation 3x plus 2 equal to 11 is true only for x equal to 3. If we put 3 in place of x in the equation, we get 3 into 3 plus 2 equal to 9 plus 2 equal to 11. So we say x equal to 3 is a solution of the equation. Hence, the value of the variable in an equation for which the equation is true is called the solution or root. Rules for solving linear equations in one variable. The same quantity can be added or subtracted to or from both sides of an equation without changing its equality. For example, to solve x plus 2 equal to 11, we subtract 2 from both sides. x plus 2 minus 2 equal to 11 minus 2, x equal to 9. Both sides of an equation may be multiplied or divided by the same non-zero number without changing its equality. For example, to solve 3x equal to 18, we divide both sides by 3. 3x upon 3 equal to 18 upon 3, x equal to 6. If ax plus b upon cx plus d equal to r upon s, then s into ax plus b equal to r into cx plus d, where ax plus b is not equal to 0, cx plus d is not equal to 0, r is not equal to 0, and s is not equal to 0. This process is called cross multiplication. Any term of an equation may be taken from one side to the other with a change in its sign. This does not affect the equality of the statement. This process is called transposition. The sign is changed from plus to minus, minus to plus, multiply to divide, divide to multiply. Solving a linear equation. Case 1. When variable is only on one side of the equality. Example. Solve and check the given equation 3x plus 5 equal to 20. Solution. 3x plus 5 equal to 20. 3x plus 5 minus 5 equal to 20 minus 5. Subtracting 5 from both sides. 3x equal to 15. 3x upon 3 equal to 15 upon 3. Dividing both sides by 3. X equal to 5 is a solution. Check LHS equal to 3x plus 5. Substituting the value of x equal to 3 into 5 plus 5 equal to 15 plus 5 equal to 20. RHS equal to 20. LHS equal to RHS. Case 2. When variable is on both sides of the equality. Example. Solve and check 3x plus 2 upon 3 equal to 2x plus 1. Solution. 3x plus 2 upon 3 equal to 2x plus 1. 3x minus 2x equal to 1 minus 2 upon 3. Bringing all the variable terms to one side, that is LHS, and constants on RHS by transposing. X equal to 1 upon 3. Check LHS equal to 3x plus 2 upon 3 equal to 3 into 1 upon 3 plus 2 upon 3 equal to 1 plus 2 upon 3 equal to 5 upon 3. RHS equal to 2x plus 1 equal to 2 into 1 upon 3 plus 1 equal to 2 upon 3 plus 1 equal to 2 plus 3 upon 3 equal to 5 upon 3. Hence, LHS equal to RHS. Solve the following equations and check the result. Solve the following equations. Applications of linear equations. Many problems in almost all topics of maths involve relationship among known quantities, numbers or constants, and unknown quantities, variables. The problems are often stated in words and hence also known as word problems. To solve a word problem, first a suitable equation containing both variables and constants is framed. Then, a suitable solution to this equation is found that satisfies the given word problem. We need to follow the steps mentioned below to solve a word problem. Step 1. Read the problem carefully and note down what is given and what is required to be found out. Step 2. Denote the unknown quantity by some English letters like X, Y, Z, A, P, and etc. Step 3. Translate the statements of the problem into mathematical statements. Step 4. Understand the relationship between the variables and constants and accordingly frame an equation containing variables and constants. Step 5. Solve the equation using any one of the methods discussed in this chapter so far. Step 6. Check whether the solution obtained in Step 5 satisfies the conditions of the word problem. Example: a number when added to its half gives 72. Find the number. Solution: let the unknown number be x. Half of the number equal to x upon 2. According to the question, x plus x upon 2 equal to 72. 2x plus x upon 2 equal to 72. By taking LCM, 3x equal to 72 into 2, x equal to 72 into 2 upon 3, x equal to 24 into 2, x equal to 48. So the number is 48. Example: the sum of 3 consecutive multiples of 7 is 777. Find the numbers. Solution: let the first multiple of 7 be x. The other two will be x plus 7 and x plus 14. According to the question, x plus 7 plus x plus 14 equal to 777. X plus 7 plus x plus 14 equal to 777. 3x plus 21 equal to 777. 3x equal to 777 minus 21. 3x equal to 756. X equal to 756 upon 3. X equal to 252. So the first number is 252. Second number is 252 plus 7 equal to 259. And the third number is 252 plus 14 equal to 266. Thus the three numbers are 252, 259, 266. Multiple choice questions. Chapter 9. Percentage and its applications. Percentage. The word percent means per hundred or out of 100. The symbol is used for percent. Example: Rahul got 65% marks in mathematics in his first semester examination. Here, 65% marks means 65 marks out of 100. Conversion. Converting a percentage into a fraction. Percent can be expressed as a fraction with 100 as the denominator. Example: 300% equal to 300 upon 100 equal to 3 upon 1 equal to 3 in lowest term. 12% equal to 12 upon 100 equal to 3 upon 25 in lowest term. Converting a fraction into a percentage. To convert a fraction into a percentage, multiply the fraction by 100 and put the sign. Example: 3 upon 25 equal to 3 upon 25 into 100% equal to 12%. 1 upon 3 equal to 1 upon 3 into 100% equal to 33 1 upon 3%. Converting a percentage into a decimal. To express a percent as a decimal, divide the percent by 100. Remove the percentage symbol and express the resultant as a decimal. Example: 47% equal to 47 upon 100 equal to 0.47. 28.6% equal to 28.6 upon 100 equal to 0.286. Converting a decimal into a percentage. To convert a decimal into a percentage, multiply the decimal by 100 and put percentage sign. Example: 0.65 equal to 0.65 into 100% equal to 65%. 0.082 equal to 0.082 into 100% equal to 8.2%. Converting a percentage into a ratio. To express a percent as a ratio, write the percent as a fraction in its lowest term and then write the ratio corresponding to the fraction obtained. Example: 48% equal to 48 upon 100 equal to 24 upon 50 equal to 12 upon 25 equal to 12 is to 25. 89% equal to 89 upon 100 equal to 89 is to 100. Converting a ratio into a percentage. To convert a ratio into a percentage, first convert the given ratio into a fraction and then to a percentage by multiplying the fraction by 100. Example: 1:4 equal to 1 upon 4 equal to 1 upon 4 into 100% equal to 25%. 1:8 equal to 1 upon 8 equal to 1 upon 8 into 100% equal to 12.5%. Finding percentage of a given quantity. To find the percentage of a given quantity, change the percentage into fraction and multiply by the given quantity. Example: find 60% of 16. Solution: 60% of 16 equal to 16 into 60 upon 100 equal to 48 upon 5 equal to 9.6. Expressing one quantity as percentage of other quantity. We can express one quantity as percentage of other quantity by using the following formula. Percentage equal to one quantity upon other quantity into 100%. Example: find 100 gram as a percentage of 5 kilogram. Solution: 5 kilogram equal to 5 into 1000 gram equal to 5000 gram. Therefore, required percentage equal to 100 upon 5000 into 100% equal to 2%. Example: convert the following: A. 1 11 upon 16 into percent, B. 2 1 upon 12% into fraction. Solution: A. 1 11 upon 16 equal to 27 upon 16 equal to 27 upon 16 into 100% equal to 2700 upon 16% equal to 168.75%. B. 2 1 upon 12 equal to 25 upon 12% equal to 25 upon 12 into 1 upon 100 equal to 1 upon 48. Example: if 31% of a number is 93, find the number. Solution: let the number be x. Then 31% of x equal to 93. 31 upon 100 into x equal to 93. X equal to 93 into 100 upon 31. X equal to 300. Thus, the number is 300. Example: what percent of 20 is 40? Solution: let x be the required percent. Then x percent of 20 equal to 40. X upon 100 into 20 equal to 40. X equal to 40 upon 20 into 100. X equal to 200%. Example: an alloy contains 38% copper, 28% zinc, and the rest is nickel. Find each quantity in grams in a sample of 1 kilogram alloy. Solution: copper equal to 38%, zinc equal to 28%, nickel equal to 100 minus 38 plus 28% equal to 34%. Quantity of copper in 1 kilogram of alloy equal to 38% of 1 kilogram equal to 38 upon 100 into 1000 gram equal to 380 gram. Quantity of zinc in 1 kilogram of alloy equal to 28% of 1 kilogram equal to 28 upon 100 into 1000 gram equal to 280 gram. Quantity of nickel in 1 kilogram of alloy equal to 34% of 1 kilogram equal to 34 upon 100 into 1000 gram equal to 340 gram. Finding increase or decrease percentage. Increase percentage equal to increased value upon original value into 100. Decrease percentage equal to decreased value upon original value into 100. Example, Rohan gets 500 rupees as pocket money every month. If this is increased by 10%, then how much will he get as pocket money? Solution. Let the increase in pocket money equal to X rupees. Rohan's initial pocket money equal to 500 rupees. Percentage increase equal to increase upon original pocket money into 100. 10 equal to X upon 500 into 100. X equal to 50. Therefore, Rohan's new pocket money will be 500 plus 50 rupees equal to 550 rupees. Convert. Find. Find X if profit and loss. In buying and selling of things, the two terms cost price and selling price are often used. The price at which an article is purchased is called the cost price. In short, it is written as CP. And the price at which an article is sold is called the selling price. In short, it is written as SP. Profit. If the selling price is more than the cost price, then the seller earns a profit or a gain. Profit equal to SP minus CP. SP equal to profit plus CP. CP equal to SP minus profit. Loss. If the selling price is less than the cost price, then the seller suffers a loss. Loss equal to CP minus SP. CP equal to SP plus loss. SP equal to CP minus loss. Overhead expenses. Overhead expense is any expenditure incurred by a trader like transport, rent of godown, finishing or polishing costs and repair, etc. Example, Aman bought a car for 45,000 rupees and spent 7,500 rupees on its repairing. This amount will be added to the cost price of the car, and 45,000 plus 7,500 rupees equal to 52,500 rupees will be considered as the actual cost price. The amount spent on repair is also called overheads. Profit or loss percent. Profit or loss percent is always expressed as a percentage of the cost price. We know that if SP is greater than CP, then the seller earns a profit. Profit percentage equal to profit upon CP into 100. SP equal to 100 plus profit percentage upon 100 into CP. CP equal to 100 upon 100 plus profit percentage into SP. If SP is less than CP, then the seller suffers a loss. Loss percentage equal to loss upon CP into 100. SP equal to 100 minus loss percentage upon 100 into CP. CP equal to 100 upon 100 minus loss percentage into SP. Example, Raghav bought an old car for 65,500 rupees and spent 12,500 rupees on its repair. He then sold it for 84,500 rupees. Find his profit or loss percent. Solution. CP of the car equal to 65,500 rupees. Overhead expenses, repair, equal to 12,500 rupees. Total CP equal to 65,500 plus 12,500 rupees equal to 78,000 rupees. SP equal to 84,500 rupees. Since SP is greater than CP, therefore Raghav gets a profit. Profit equal to 84,500 minus 78,000 rupees equal to 6,500 rupees. Profit percentage equal to 6,500 upon 78,000 into 100 equal to 25 upon 3 equal to 8 1 upon 3%. Hence, Raghav gained a profit of 8 1 upon 3%. Example. The selling price of 12 bottles is equal to the cost price of 15 bottles. Find the profit or loss percent. Solution. Let the CP of 1 bottle be Y rupees. CP of 12 bottles equal to 12 into Y rupees equal to 12 Y rupees. SP of 12 bottles equal to CP of 15 bottles equal to 15 Y rupees. Since SP is greater than CP, hence there is a profit. Profit equal to SP minus CP equal to 15Y minus 12Y rupees equal to 3Y rupees. Profit percentage equal to profit upon CP into 100 equal to 3Y upon 12Y into 100 equal to 25%. Hence, there is a profit of 25%. Marked price and discount. In many shops, every article which is to be sold has a price written on it. This price which is tagged or listed to it or marked on it is called the marked price or list price. It is written in short as MP. But if due to some reason the retailer is not able to sell the articles at their MP, or if he wants to improve his sales by attracting more customers or to clear the old stock, he offers a certain rebate on the MP. This rebate, which is usually given as a percent of MP, is called discount. Sale price, marked price relationship. Sale price equal to MP minus discount. Discount percentage equal to discount upon MP into 100. Example. The marked price of an article is 850 rupees and the retailer gives a discount of 6% on it. Find the sale price of the article. Solution. MP of the article equal to 850 rupees. Discount percentage equal to 6%. Actual discount equal to 6% of MP equal to 6 upon 100 into 850 rupees equal to 51 rupees. Sale price equal to MP minus discount equal to 850 minus 51 rupees equal to 799 rupees. Therefore, the sale price of the article is 799 rupees. Example. The marked price of an article is 2,500 rupees. If after giving a discount of 10%, a trader still gets a profit of 12 1 upon 2%, find the cost price of the article. Solution. MP equal to 2,500 rupees. Discount percentage equal to 10%. Actual discount equal to 10% of MP equal to 10 upon 100 into 2,500 rupees equal to 250 rupees. Sale price equal to MP minus discount equal to 2,500 minus 250 rupees equal to 2,250 rupees. Profit percentage equal to 12 1 upon 2%, CP equal to 100 upon 100 plus profit percentage into SP equal to 100 upon 100 plus 12 1 upon 2 into 2,250 rupees equal to 100 into 2,250 into 2 upon 225 rupees equal to 2,000 rupees. Hence, the cost price of the article is 2,000 rupees. Note, discount is always calculated on MP. In case there is no discount, then MP is the SP. Value added tax. The central government and all the state governments provide various facilities to the public and need money for these welfare activities. They collect this money through different types of taxes like sales tax, income tax and value added tax, VAT. Sales tax and value added tax are added to the selling price of the article. If the sale involves discount, then after subtracting discount from MP, sales tax is added to the SP. In case there is no discount, then sales tax or VAT is added to the MP. Example: the list price of a TV set is 19,750 rupees. If the rate of VAT is 4%, find the selling price of the TV set. Solution: list price of the TV set equal to 19,750 rupees. Rate of VAT equal to 4%. VAT equal to 4% of 19,750 rupees equal to 4 upon 100 into 19,750 rupees equal to 790 rupees. SP of TV set equal to 19,750 plus 790 rupees equal to 20,540 rupees. Example: Sonia purchased the following items from a departmental store. A. 1 pair sport shoes for 850 rupees, VAT 8%. B. Leather jacket for 2,550 rupees, VAT 10%. C. Cotton clothes for 800 rupees, VAT 5%. D. Provisions for 2,250 rupees, VAT 6%. Calculate the total amount of the bill. Solution: A. Cost of sport shoes equal to 850 rupees, VAT equal to 8%. VAT equal to 8% of 850 rupees equal to 8 upon 100 into 850 rupees equal to 68 rupees. SP of shoes equal to 850 plus 68 rupees equal to 918 rupees. B. Cost of leather jacket equal to 2,550 rupees. VAT equal to 10%. VAT equal to 10% of 2,550 rupees equal to 10 upon 100 into 2,550 rupees equal to 255 rupees. SP of leather jacket equal to 2,550 plus 255 rupees equal to 2,805 rupees. C. Cost of cotton clothes equal to 800 rupees. VAT equal to 5%. VAT equal to 5% of 800 rupees equal to 5 upon 100 into 800 rupees equal to 40 rupees. SP of cotton clothes equal to 800 plus 40 rupees equal to 840 rupees. D. Cost of provisions equal to 2,250 rupees. VAT equal to 6%. VAT equal to 6% of 2,250 rupees equal to 6 upon 100 into 2,250 rupees equal to 135 rupees. SP of provisions equal to 2,250 plus 135 rupees equal to 2,385 rupees. Therefore, total amount of the bill equal to 918 plus 2,805 plus 840 plus 2,385 rupees equal to 6,948 rupees. Multiple choice questions. Chapter 10. Compound Interest. Simple interest, SI. When the money is borrowed or lent, some extra money is paid to the lender for the use of borrowed money for a given period of time at a given rate. This extra money paid to the lender is called interest. The money borrowed or lent is called the principal, P. The rate at which the interest is calculated is called the rate of interest per annum, R. The amount A is the sum of the principal, P, and the interest, I. If T is the time for which the principal is borrowed or lent, then SI equal to P into R into T upon 100, where P equal to principal, R equal to rate of interest, T equal to time. It can be transformed in the following ways: P equal to SI into 100 upon R into T, R equal to SI into 100 upon P into T, T equal to SI into 100 upon P into R. Amount A equal to principal plus interest, I. Example: if a sum of 1,500 rupees is borrowed for 4 years at the rate of 9% per annum, find the simple interest and the amount to be paid after 4 years. Solution: the formula used to calculate the simple interest is SI equal to P into R into T upon 100. Given principal P equal to 1,500 rupees, time T equal to 4 years, rate R equal to 9%. Therefore, SI equal to 1,500 into 9 into 4 upon 100 equal to 540. Simple interest for 4 years equal to 540 rupees. Amount to be paid after 4 years equal to principal plus SI for 4 years equal to P plus SI equal to 1,500 rupees plus 540 rupees equal to 2,040 rupees. Compound interest, CI. In the case of simple interest, the amount of interest earned remains the same every year. However, in practice, the method according to which banks, post offices, insurance companies, and other financial institutions calculate interest is different from the one given above. These institutions calculate the interest for 1 year, then the yearly interest is added to the principal, and the amount so obtained is treated as the principal for calculating the interest for the second year, and so on. This process is repeated until the amount for the whole loan period is found. The difference between the loan amount and the original amount or principal or money borrowed is called the compound interest or CI. Let us try to understand the concept of compound interest by taking an example. Suppose I borrow 10,000 rupees from a bank for some business purpose at the rate of 10% per annum for 1 year. Then, principal equal to 10,000 rupees, rate equal to 10% per annum, time equal to 1 year. Therefore, interest to be paid by me at the end of 1 year equal to 10,000 into 10 into 1 upon 100 rupees equal to 1,000 rupees. Therefore, amount paid by me at the end of 1 year equal to principal plus interest equal to 10,000 rupees plus 1,000 rupees equal to 11,000 rupees. But if due to some reasons I am unable to return the money at the end of 1 year, the bank will calculate the interest at the end of second year as follows. Principal for the second year equal to 11,000 rupees. Interest for the second year equal to 11,000 into 10 into 1 upon 100 rupees equal to 1,100 rupees. Therefore, amount to be paid by me at the end of second year equal to 11,000 rupees plus 1,100 rupees equal to 12,100 rupees. Again, if I am unable to return the money at the end of second year, then the bank will calculate the interest for the third year as follows. Principal for third year equal to 12,100 rupees. Therefore, interest for third year equal to 12,100 into 10 into 1 upon 100 rupees equal to 1,210 rupees. Therefore, amount to be paid by me at the end of third year equal to 12,100 rupees plus 1,210 rupees equal to 13,310 rupees. So it is clear that the amount at the end of first year becomes the principal for the second year, and the amount at the end of second year becomes the principal for the third year, and so on. If the interest is being calculated in this manner, then we say that the interest charged is compound interest. Here the principal is not the same throughout the loan period. Now, total compound interest paid by me after 3 years equal to amount minus principal equal to 13,310 minus 10,000 rupees equal to 3,310 rupees, and SI after 3 years equal to 10,000 into 10 into 3 upon 100 rupees equal to 3,000 rupees. The compound interest on 10,000 rupees at 10% per annum for 3 years is greater than the simple interest on the same principal, at the same rate and for the same time. Hence, we can say that the compound interest is always more than the simple interest for the same time and at the same rate of interest. Example: find the amount and compound interest on 2,500 rupees for 3 years at 10% per annum compounded annually. Solution: given principal P equal to 2,500 rupees, rate R equal to 10% per annum. Interest for the first year equal to P into R into T upon 100 equal to 2,500 into 10 into 1 upon 100 equal to 250 rupees. Therefore, amount at the end of the first year equal to 2,500 plus 250 rupees equal to 2,750 rupees. Principal for the second year equal to amount of the first year equal to 2,750 rupees, rate equal to 10%. Interest for the second year equal to P into R into T upon 100 equal to 2,750 into 10 into 1 upon 100 equal to 275 rupees. Therefore, amount at the end of the second year equal to 2,750 plus 275 rupees equal to 3,025. Principal for the third year equal to amount of the second year equal to 3,025 rupees, rate equal to 10%. Interest for the third year equal to P into R into T upon 100 equal to 3,025 into 10 into 1 upon 100 equal to 302.50 rupees. Therefore, amount at the end of the third year equal to 3,025 plus 302.50 rupees equal to 3,327.50 rupees, and compound interest of 3 years equal to 3,327.50 minus 2,500 rupees equal to 827.50 rupees. Remember, SI and CI are equal for the first year, but for calculating compound interest, the amount at the end of first year becomes the principal for the second year. The amount at the end of second year becomes the principal for the third year, and so on. The total compound interest is equal to the sum of interest for all the years the money remained with the borrower. Calculating amount and compound interest. In the previous section of this chapter, we have learned to calculate compound interest. The method used to calculate CI is very lengthy. Let us learn a shorter way of finding compound interest. Let principal equal to P, rate of interest equal to R%, time equal to 1 year. Interest for the first year equal to P into R into T upon 100 equal to P into R upon 100. Amount at the end of the first year equal to P plus P into R upon 100 equal to P into 1 plus R upon 100. Principal for the second year P1 equal to P into 1 plus R upon 100. Interest for the second year equal to P1 into R into T upon 100 equal to P1 into R upon 100. Amount at the end of the second year equal to P1 plus P1 into R upon 100 equal to P1 into 1 plus R upon 100 equal to P into 1 plus R upon 100 into 1 plus R upon 100, as P1 equal to P into 1 plus R upon 100 equal to P into 1 plus R upon 100 whole square equal to P2. Say, principal for the third year equal to P2, interest for the third year equal to P2 into R into T upon 100 equal to P2 into R upon 100. Amount at the end of the third year equal to P2 plus P2 into R upon 100 equal to P2 into 1 plus R upon 100 equal to P into 1 plus R upon 100 whole square into 1 plus R upon 100, as P2 equal to P into 1 plus R upon 100 whole square equal to P into 1 plus R upon 100 whole cube. Continuing the above procedure for the fourth year, we get amount at the end of 4 years equal to P into 1 plus R upon 100 wholes raised to the power 4. The above formula for calculating the amount for n years can be generalized in the following way. Amount at the end of n years equal to P into 1 plus R upon 100 wholes raised to the power n. Therefore, for principal P that earns compound interest at the rate of R% per annum for n years, the amount A would be A equal to P into 1 plus R upon 100 wholes raised to the power n. Compound interest CI equal to A minus P. Example, find the CI on 25,000 rupees for 2 years at 8% per annum compounded annually. Solution. Given principal P equal to 25,000 rupees, rate R equal to 8% per annum, time n equal to 2 years. Substituting these in the formula, A equal to P into 1 plus R upon 100 wholes raised to the power n, we get A equal to 25,000 rupees into 1 plus 8 upon 100 whole square equal to 25,000 rupees into 27 upon 25 into 27 upon 25 equal to 29,160 rupees. Amount equal to 29,160 rupees. Compound interest equal to A minus P equal to 29,160 minus 25,000 rupees equal to 4,160 rupees. Using formula, calculate the amount and the CI in each of the following. Applications of compound interest. The formula for finding the compound interest can be applied in daily life situations like increase or decrease in population, the value of an item if its price increases or decreases, the growth of bacteria if the rate of growth is known, If the value of a vehicle or a machine decreases, depreciates. From the above examples, it is clear that the time period plays an important role in the growth of them, which may be positive or negative role in the growth. When R is positive, that is growth rate is positive, then A equal to P into 1 plus R upon 100 whole raised to the power n. When R is negative, that is growth rate is negative, then A equal to P into 1 minus R upon 100 whole raised to the power n. Example: the present population of a town is 31,250. If the annual increase in population is 4%, what will be the population of the town after 3 years? Solution: present population P equal to 31,250 time T equal to 3 years. Rate R equal to 4%. We have A equal to P into 1 plus R upon 100 whole raised to the power n. A equal to 31,250 into 1 plus 4 upon 100 whole cube equal to 31,250 into 1 plus 1 upon 25 whole cube equal to 31,250 into 26 upon 25 whole cube equal to 31,250 into 26 upon 25 into 26 upon 25 into 26 upon 25 equal to 35,152. Therefore, hence, after 3 years, the population of the town will be 35,152. Multiple choice questions. Fill in the blanks. Multiple choice questions. Chapter 11. Direct and indirect variations. Variation. If the values of two quantities depend on each other in such a way that a change in one results in a corresponding change in the other, then the two quantities are said to be in variation. Observe the following examples. As the number of articles bought increases, their cost also increases. Number of articles bought and their cost increases together. As the number of men increases, the number of days taken to finish the same work decreases. Increase in the number of men decreases the number of days. Thus, two quantities may be related to each other in two ways. In first case, both the quantities increase or decrease together, and in the second case, if one quantity increases, other decreases, and vice versa. So we can say that there are two types of variations: direct variation, indirect or inverse variation. Direct variation. Two quantities vary directly. If the increase or decrease in one quantity causes the increase or decrease in another quantity. Consider the following examples. A tailor needs 6-meter cloth for stitching 3 shirts. How much cloth will he require for stitching 6 shirts? He will require 12 meter of cloth. Since the number of shirts is doubled, the cloth required is also doubled. Therefore, when the number of shirts is increased, the cloth required is also increased. Study the following table. Number of shirts M. Cloth required in meter Y. 3, 6, 6, 12, 9, 18, 12, 24, 15, 30, 18, 36, 21, 42. From the above table, we observe that as the number of shirts increases, the quantity of cloth required also increases. Also, the increase is such that the ratio x upon y of two quantities, x and y, does not change. It remains constant. That is, x upon y equal to 3 upon 6, equal to 6 upon 12, equal to 9 upon 18, equal to 12 upon 24, equal to 15 upon 30, equal to 18 upon 36, equal to 21 upon 42, equal to 1 upon 2. Thus, the ratio x upon y equal to constant k, or x equal to ky, where k is called the constant of variation. Therefore, two quantities x and y are said to be in direct variation if they increase or decrease together in such a way that their ratio x upon y remains constant and is always positive. Example, check whether P and Q vary directly or not. If yes, then find the constant of variation. P, Q, 6, 12, 8, 16, 12, 24, 15, 30. Solution. First find the ratio P upon Q. P upon Q equal to 6 upon 12, equal to 8 upon 16, equal to 12 upon 24, equal to 15 upon 30, equal to 1 upon 2. We observe that the ratio P upon Q is constant, that is 1:2. Thus, P and Q vary directly and the constant of variation is 1 upon 2. In the following tables, identify those in which P and Q vary directly with respect to each other. Also, find the constant of variation. If x and y vary directly, find the constant of variation k and complete the tables. If the cost of 7 kg potatoes is 84, find indirect or inverse variation. Two quantities are said to vary inversely or indirectly if the increase or decrease in one quantity causes the decrease or increase in the other quantity, respectively. Consider the given example. Suppose a child wants to give return gifts to his friends who will be attending his birthday party. His parents have given him 500 rupees for the purchase of these gifts. If he has invited only 5 friends, he needs to buy only 5 gifts, so he can purchase gifts worth 100 rupees each. But if he has invited 25 friends, he needs to buy 25 gifts, each worth 20 rupees. If the number of friends is 10, he needs to buy 10 gifts worth 50 rupees each. And so on. The following table shows this variation between the number and cost of gifts. Number of gifts, cost of each gift in rupee. 5, 100, 10, 50, 20, 25, 25, 20, 50, 10. We notice that if the number of gifts is more, the cost of each gift is less. And if the number of gifts is less, then the cost of each gift is more. The ratio by which the number of gifts increases from 10 to 50 is 1:5, and the ratio by which the corresponding cost of gifts reduces from 50 rupees to 10 rupees is 5:1. This means that the two ratios are inverse of each other. Also, in each case, the product of the corresponding values of the two quantities is constant, that is, 5 into 100 equal to 10 into 50 equal to 20 into 25 and up to equal to 500. So, two quantities are said to vary inversely if there exists a relation between them such that xy equal to k being the constant of variation. If x1, x2 are two values of x and y1, y2 are the corresponding values of y, then x1 y1 equal to x2 y2 equal to k. If x varies inversely with y or x is in inverse proportion to y, then x is proportional to 1 upon y. Example, in the following table, if x varies inversely with y, find the missing entries. Solution. Let us denote the missing entries as y2, y3, x4, x5. Since it is a case of inverse variation, taking x1 equal to 18, y1 equal to 40, and x2 equal to 32, and using the relation x1 y1 equal to x2 y2, we get 18 into 40 equal to 36 into y2. y2 equal to 18 into 40 upon 36 equal to 20. Taking x3 equal to 24 and using the relation x1 y1 equal to x3 y3, we get 18 into 40 equal to 24 into y3. y3 equal to 18 into 40 upon 24 equal to 30. Taking y4 equal to 16 and using x3 y3 equal to x4 y4, we get 24 into 30 equal to x4 into 16. x4 equal to 24 into 30 upon 16 equal to 45. Taking y5 equal to 60 and using x4 y4 equal to x5 y5, we get 45 into 16 equal to x5 into 60. x5 equal to 45 into 16 upon 60 equal to 12. Therefore, the missing entries are 20, 30, 45 and 12. Example, if 52 men can do a piece of work in 27 days, how long will 39 men take to complete the same work? Solution. If the number of men decreases, the number of days will increase. So, it is a case of inverse variation. Taking the number of days to be y, we make a table of the given values. Taking x1 equal to 52, x2 equal to 39, y1 equal to 27 and using x1 y1 equal to x2 y2, we get 52 into 27 equal to 39 into y2. y2 equal to 52 into 27 upon 39 equal to 36. So, 39 men will do the work in 36 days. Time and work. The basic rules for solving time and work problems are: if a person can do a work in X days, then the work done by the person is 1 day equal to 1 upon X. If a person's 1 day work equal to 1 upon X, then the person can complete the work in X days. If A can complete a work in X days and B can do in Y days, then A's 1 day work equal to 1 upon X of the whole work. B's 1 day work equal to 1 upon Y of the whole work. If A upon B work together to do the same work, then in 1 day, they will do 1 upon X plus 1 upon Y of the whole work. Example, Sanjay can complete a piece of work in 10 days and Ajay can complete the same piece of work in 15 days. If they work together, in how many days will the work be completed? Solution. Sanjay can complete the work in 10 days. Sanjay's 1 day work equal to 1 upon 10 of the work. Ajay can complete the work in 15 days. Ajay's 1 day work equal to 1 upon 15 of the work. Therefore, Sanjay's and Ajay's 1 day work equal to 1 upon 10 plus 1 upon 15 equal to 3 plus 2 upon 30 equal to 5 upon 30 equal to 1 upon 6. Ajay and Sanjay working together in 1 day can finish 1 upon 6 of the work. Therefore, Sanjay and Ajay working together can finish the work in 6 days. Example, A can do a piece of work in 30 days and B alone can do it in 20 days. They work together for 4 days and then B leaves the job. In how many days will A finish the remaining work? Solution. Work done by A in 1 day equal to 1 upon 30 and work done by B in 1 day equal to 1 upon 20. Work done in 1 day if A and B work together equal to 1 upon 30 plus 1 upon 20 equal to 2 plus 3 upon 60 equal to 5 upon 60 equal to 1 upon 12. Work done in 4 days if A and B work together equal to 4 into 1 upon 12 equal to 1 upon 3. Work still to be done equal to 1 minus 1 upon 3 equal to 2 upon 3. Now A has to finish 2 upon 3 of the work. Hence, number of days A needs to finish the remaining work equal to 2 upon 3 divided by 1 upon 30 equal to 2 upon 3 into 30 equal to 20 days. Multiple choice questions. Chapter 12. Properties of quadrilaterals. Polygons. A simple closed curve made up of only line segments is called a polygon. We can classify the polygons according to the number of sides or vertices they have. A polygon has at least 3 sides. Look at the table shown below. Number of sides or vertices. Classifications. Sample figure. 3. Triangle. 4. Quadrilateral. 5. Pentagon. 6. Hexagon. 7. Heptagon. 8. Octagon. 9. Nonagon. 10. Decagon. A polygon which has n sides is called a n-gon. Diagonals of the polygon. The line segment formed by joining non-adjacent vertices are called diagonals of the polygon. In the polygon shown alongside the line segments AC, AD, BD, BE and CE are the diagonals of the polygon. Convex and concave polygons. Convex polygon. A polygon in which the line segment joining any 2 points, diagonals, always lies in the interior of the polygon is called a convex polygon. Or, a polygon in which each interior angle is less than 180 degree is called a convex polygon. Concave polygon. A polygon in which the line segment joining any 2 points does not lie inside the polygon completely is a concave polygon. Or, a polygon in which at least one interior angle is greater than 180 degree is called a concave polygon. Find the number of sides of a regular polygon when each of its angles has a measure of. Find the value of x in each of the following figures. Types of quadrilaterals. Quadrilaterals are classified on the basis of the nature of their sides and angles with the following names. Trapezium. A trapezium is a quadrilateral having only one pair of parallel sides. Quadrilateral ABCD shown in figure is a trapezium having sides AB parallel to DC. A trapezium also has a relationship among the angles formed along its parallel sides. According to this relationship for sides AB parallel to DC in trapezium ABCD, angle A plus angle D equal to 180 degree and angle B plus angle C equal to 180 degree. Isosceles trapezium. An isosceles trapezium is a quadrilateral in which one pair of opposite sides are parallel and the sides which are not parallel are equal. Quadrilateral PQRS, shown in figure, is an isosceles trapezium. Its sides PQ and SR are parallel, and non-parallel sides PS and Q are equal. Kite. A kite is a quadrilateral which has both pairs of adjacent sides equal. Quadrilateral PQRS, shown in figure, is a kite. The equal pairs of adjacent sides in kite PQRS are PQ equal to PS and RS equal to RQ. Its diagonal are perpendicular to each other. Parallelogram. A parallelogram is a quadrilateral in which both pairs of opposite sides are parallel. Quadrilateral ABCD, shown in figure, is a parallelogram because it has AB parallel to DC, AD parallel to BC, and AB equal to DC, AD equal to BC. Properties of a parallelogram. A parallelogram has the following properties. Its opposite sides are equal. Its opposite angles are equal. Its diagonals bisect each other. Its adjacent angles are supplementary. Let us prove these properties in a parallelogram, say PQRS, shown in figure. Multiple choice questions. Chapter 13. Practical Geometry. Construction of quadrilaterals. We know that a quadrilateral is a closed plane figure formed by 4 line segments which do not intersect each other except at their endpoints. The shape and size of a quadrilateral or any other polygon are defined by its elements. A quadrilateral has the following elements: 4 sides, 4 angles, 2 diagonals. Thus, a quadrilateral has 10 elements. To construct a unique quadrilateral, at least 5 of its elements must be given. Case 1. To construct a quadrilateral when its 4 sides and 1 diagonal are given. Example: construct a quadrilateral ABCD in which AB equal to 3 cm, BC equal to 4 cm, DC equal to 2 cm, AD equal to 3.5 cm, and AC equal to 5 cm. Solution. First draw a rough figure of the quadrilateral. Then check is it possible to draw a triangle ABC with sides AB equal to 3 cm, BC equal to 4 cm, and AC equal to 5 cm. AB plus BC equal to 3 plus 4 equal to 7, which is greater than AC. As sum of the 2 smaller sides is greater than the third side, so the construction of triangle is possible. This means construction of quadrilateral is also possible. Steps of construction. Draw AC equal to 5 cm. With A as center and a radius AB equal to 3 cm, draw an arc above AC with C as center and a radius BC equal to 4 cm. Draw another arc cutting the first arc at B and join AB and BC with A as center and radius AD equal to 3.5 cm. Draw an arc below AC with C as center and radius CD equal to 2 cm. Draw another arc cutting the first arc at D and join AD and DC. Thus, ABCD is the required quadrilateral. Case 2. To construct a quadrilateral when 3 sides and both diagonals are given. Example: Construct a quadrilateral PQRS in which PQ equal to 5.5 cm, QR equal to 4 cm, SR equal to 3.5 cm, PR equal to 6 cm, SQ equal to 5.8 cm. Solution. Draw a rough figure of the quadrilateral. Steps of construction. Draw PQ equal to 5.5 cm with P as center and radius PR equal to 6 cm. Draw an arc with Q as center and radius QR equal to 4 cm. Draw another arc cutting first arc at R. Join PR and QR with R as center and radius equal to 3.5 cm. Draw an arc with Q as center and radius equal to 5.8 cm. Draw another arc cutting the first arc at S. Join PS, RS and QS. Thus, PQRS is the required quadrilateral. Construction of special quadrilaterals. Sometimes you need to construct these types of quadrilaterals even when you are not given the required number of elements necessary for constructing a unique quadrilateral. While constructing special quadrilaterals, you are expected to use not only the given data, but also the properties of the special quadrilaterals. You should always clearly mention the property being used and the manner of using it. Examples. Construct a rhombus BOLD, where BO equal to 6 cm and angle B equal to 80 degree. Solution. Since BOLD is a rhombus, therefore all of its sides are equal. Therefore, BO equal to OL equal to LD equal to DB equal to 6 cm. Since adjacent angles are supplementary in a rhombus, we have angle B plus angle O equal to 180 degree. Angle O equal to 100 degree. Now draw a rough figure of rhombus BOLD. Steps of construction. Step 1. Draw a line segment BO equal to 6 cm. Step 2. Using a protractor, construct angle XBO equal to 80 degree at B. Step 3. Again using a protractor, construct angle YOB equal to 100 degree at O. Step 4. With B as center and radius equal to 6 cm, draw an arc to cut BX at D. Step 5. With O as center and radius equal to 6 cm, draw an arc to OY at L. Step 6. Join DL. Thus, BOLD is the required rhombus. Chapter 14. Visualizing solid shapes. Solid figures. Cuboid. A solid bounded by 6 rectangular faces is called a cuboid. A cuboid has 6 faces, 8 vertices and 12 edges. For example, a matchbox, a brick, a book, an almirah, etc. Cube. A cuboid whose length, breadth and height are all equal is called a cube. A cube also has 6 faces, 8 vertices and 12 edges. For example, die, sugar cube, ice cube, etc. Cylinder. Solids like circular pillars, circular pipes and road rollers are called cylinders. A cylinder has 2 flat circular faces and a curved surface. It has no vertices. A cylinder has 2 curved edges. Cone. Solids like an ice cream cone, a tent, and a clown's cap are in the shape of a cone. A cone has a curved surface and 1 flat circular face. A cone has 1 curved edge and 1 vertex. Sphere. Solids like a ball, a globe, and a marble are in the shape of a sphere. A sphere has no face, no edge, and no vertex. It has only curved surface. Hemisphere. Hemispheres are solids formed by cutting a sphere into two equal halves. For example, a bowl. Prism. A solid whose two bases or ends are parallel, plane polygons, and other faces are rectangles is called a prism. Triangular prism. A triangular prism has two triangular bases and three rectangular side faces. It has 9 edges and 6 vertices. Rectangular prism. A prism whose base and top are congruent rectangles and lateral faces are rectangles is called a rectangular prism. Pentagonal prism. A prism whose base and top are congruent pentagons and lateral faces are rectangle is called a pentagonal prism. Hexagonal prism. A prism whose base and top are congruent hexagonal and lateral faces are rectangles is called a hexagonal prism. Pyramid. A pyramid is a solid whose base is a plain rectilinear figure and whose side faces are triangular having a common vertex. The common vertex is called the vertex of the pyramid. Since the side faces of all pyramids are triangles, a pyramid is named after its base. Also, the number of side faces that a pyramid has is equal to the number of sides in the base. Square pyramid. It is a pyramid whose base is a square and side faces are triangles. It has 5 vertices and 8 edges. It has 5 faces of which one is a square and 4 are triangles. Triangular pyramid or tetrahedron. It is a pyramid whose base is a triangle and side faces are also triangles having a common vertex. It has 4 triangular faces, 4 vertices and 6 edges. Euler's formula. Is there any relationship between the edges, vertices, and faces of the polyhedron? Yes, this relationship was proved by Swiss mathematician Leonhard Euler, 1707 AD to 1783 AD. It states that F plus V minus E equal to 2 or F plus V equal to E plus 2. Look at the table shown below to verify it. Solid F, V, E, F plus V, E plus 2. Cube 6, 8, 12, 14, 14. Cuboid 6, 8, 12, 14, 14. Triangular prism 5, 6, 9, 11, 11. Triangular pyramid 4, 4, 6, 8, 8. Pyramid with square base 5, 5, 8, 10, 10. From the above table, we observe that the column F plus V and E plus 2 are the same. From this we can conclude that V plus F equal to E plus 2 or V plus F minus E equal to 2, where V equal to number of vertices, F equal to number of faces, E equal to number of edges. Nested solids. Many solids that we see in our daily life are actually made up of 2 or more solids. Such solids are called nested solids. Some common examples of nested solids are hut, pencil, lollipop, ice cream cone with a scoop of ice cream, tent, etc. Combination of solid shapes. We have defined the shape of an ice cream cone as a cone and a gas cylinder as a cylinder. But are these shapes exactly what we describe them? An ice cream cone is actually a cone having a hemisphere on top of it. A tent is usually a cylinder surmounted by a cone. Thus, Many of the solid shapes that we see around us are actually a combination of two or more solid shapes. Also, depending upon the angle of observation, the solid figures may look different. For example, a hut seen from different angles is shown. Its front view is of a pentagon or a rectangle surmounted by a triangle. The top view is of two parallelograms and the side view is of an overlapping rectangle and a trapezium. Depending on the angle of viewing, each one of us may have a different opinion of what the hut looks like. Therefore, these shapes are not standard shapes. Now consider a sharpened pencil. Figure. From the bottom, it looks like a hexagon. Its top view is of a point, and the side view is of a rectangle and a triangle. Does the side view change from side to side? No, all of its faces, sides, have the same shape. Now let us consider a bar of soap, washing soap. The shape of a soap bar can be described as a cuboid. Its front view and side view is of a rectangle and top view is also of a rectangle, but with ridges on it. Sometimes the brand name is etched on the top rectangle. Tabulate the number of faces, edges and vertices for the following polyhedrons. Here V stands for number of vertices, F stands for number of faces and E stands for number of edges. Nets for visualizing 3D figures. What is the shape of a shoebox? It is a cuboid. What happens when you cut or open the edges of such a box without separating any of its parts and lay the box flat on a plain surface? After opening the edges, the shape that you get is as shown in figure. The flattened shoebox, when folded along the edges shown by the dotted lines, will give us a cuboid. The shape or outline in 2 dimensions, which when folded gives us a 3-dimensional figure, is called a net. A net for a 3D shape is a sort of outline in 2 dimensions, which when folded results in a 3D shape. The following are net patterns for some 3D figures. Net pattern for a cube. Net pattern for a cuboid. Prism with a base of right-angled triangle. Prism with a base of equilateral triangle. Net pattern for a triangular prism. Net pattern for a triangular pyramid. Net pattern for a square pyramid. Net pattern for a pentagonal pyramid. Views of 3D shapes. We can look at an object by standing in front of it or by the side of it or from above. Each time we get a different view. Top view is a picture of the solid we see from the top. Front view of a solid gives a different shape as compared to the top view unless the solid is symmetrical, like cube. Side view of a solid is also different to top as well as front view. For example, the given building can have following views. Similarly, a 5 kilogram weight can have the following views. Similarly, we can get different views of figures made by joining cubes. Name the 3D figures that can be obtained by folding the following nets. Maps. Have you ever searched for a friend's house using a map drawn by him? Or have you ever searched for a doctor's clinic or a function venue using a map drawn by someone for you? If the map is something like the one shown in figure alongside, you will never reach your destination or will spend a lot of time and energy searching for it. But if the map is drawn as shown given below, searching for the place becomes easy. This is because the second map shows landmarks and gives you the correct information about the distance, when to take a left turn, and so on. A good map must have the following features. It must be drawn to a scale and the scale must be mentioned. The scale reduces the real distance proportionally to distances on the map. Standard symbols must be used. It must depict the location of a particular object or place in relation to other object or place. The map must indicate directions like north, south, etc. There is no reference or perspective in a map. Note: a map involves a fixed scale. The larger the place and the smaller the map drawn, the greater is the distance represented by 1 millimeter or kilometer. Multiple choice questions. Fill in the blanks. Chapter 15. Area. Area and perimeter of some plane figures. Let us recall the area and perimeter of some plane figures. Serial number, shape, name, area, perimeter. 1. Triangle. 1/2 BH. A plus B plus C. 2. Rectangle. L into B. 2 into L plus B. 3. Square. A square. 4A. 4. Parallelogram. BH. 2 into A plus B. 5. Circle. Pi r square. 2 pi r. Example. Find the area of the following figures. Solution. Given figure is a semicircle. Area of semicircle equal to 1/2 pi r square equal to 1/2 into 22/7 into 3.5/2 into 3.5/2 equal to 5.5 into 3.5/4 equal to 19.25/4 equal to 4.8125 meters square. B. Given figure is a parallelogram. Area of parallelogram equal to 16 into 8 equal to 128 centimeters square. C. Given figure is a triangle. Area of triangle equal to 1/2 into 14 into 7 equal to 49 centimeters square. Remember, 100 millimeters square equal to 1 centimeter square. 100 centimeters square equal to 1 decimeter square. 100 decimeters square equal to 1 meter square. 100 meters square equal to 1 decameter square. 100 decameters square equal to 1 hectometer square. 100 hectometers square equal to 1 kilometer square. The following conversions are used frequently. 10,000 centimeters square equal to 1 meter square. 10 lakh meters square equal to 1 kilometer square. Calculate the area of a trapezium in centimeters square, length of whose parallel sides and distance between them are. Area of a general quadrilateral. A general quadrilateral can be split into two triangles as shown in figure. The area of the quadrilateral can be obtained as the sum of the two triangles. For the given figure, the area of quadrilateral PQRS is equal to the sum of the areas of triangles PQR and PSR, that is, area of quadrilateral PQRS equal to area of PQR plus area of PSR equal to 1/2 into PR into H1 plus 1 upon 2 into PR into H2 equal to 1 upon 2 into PR into H1 plus H2. Area of quadrilateral equal to 1 upon 2 into D into H1 plus H2, where D is the length of one of the diagonal PR of the quadrilateral and H1 and H2 are the altitudes or perpendiculars from the two vertices opposite to this diagonal. Find the area enclosed by each of the following figures. Multiple choice questions. Chapter 16. Volumes and surface areas. Volume of a cuboid and a cube. We know that the space occupied by a solid is called its volume. The volume is indicated by the symbol V. Standard units of volume. The space occupied by a unit cube, each of whose edge is 1 centimeter long, is 1 cubic centimeter. It is written as 1 cubic centimeter or 1 centimeter cube. Cubic centimeter is the standard unit of volume. Some other standard units of volume and their relations are 1 centimeter equal to 10 millimeter, 1 centimeter cube equal to 1000 millimeter cube, 1 meter equal to 100 centimeter, 1 meter cube equal to 10 raised to the power 6 centimeter cube, 1 decimeter equal to 10 centimeter, 1 decimeter cube equal to 1000 centimeter cube, 1 meter equal to 10 decimeter, 1 meter cube equal to 1000 decimeter cube, 1 kilometer equal to 1000 meter, 1 kilometer cube equal to 10 raised to the power 9 meter cube. Capacity, that is volume of a vessel, is expressed in liters. 1 centimeter cube equal to 1 milliliter. 1000 centimeter cube equal to 1000 milliliter equal to 1 liter. 1 meter cube equal to 1000 liters equal to 1 kiloliter. Formula for volume of a cuboid and a cube. Volume V of a cuboid of length L, breadth B, height h is given as V equal to L into B into h cubic units. From the above formula, we observe that L equal to V upon B into h, B equal to V upon L into h equal to V upon L into B. In case of a cube, L equal to B equal to h. Therefore, volume of a cube equal to L into L into L equal to L cube. V equal to L cube, cubic units. Surface area of a cuboid and a cube. As a cuboid has 6 faces and each face has some area, we can define surface area as the surface area of a cuboid is the sum of the areas of all of its faces. Area of EFGH equal to area of ABCD equal to length into breadth. Area of EFGH equal to area of ABGH equal to breadth into height. Area of ADHE equal to area of BCFG equal to length into height. By adding areas of 6 surfaces, surface area of a cuboid equal to 2 into L into B plus B into H plus L into H. As measure of each edge of a cube is the same, therefore surface area of a cube equal to 6 into side square equal to 6L square. Lateral surface area of a cuboid equal to area of EFCD plus ABGH plus ADHE plus BCFG equal to 2 area of ADHE plus EFCD equal to 2 into L into H plus B into H equal to 2 into L plus B into H. LSA of a cuboid equal to 2 into L plus B into H. Lateral surface area of a cube equal to 2 into side plus side into side equal to 2 into L plus L into L equal to 4L square equal to 4 side square. LSA of a cube equal to 4L square. Area of 4 walls of a room. Let the length, breadth and height of a room be L, B and H respectively. Then, area of the 4 walls of the room equal to 2H into L plus B. Diagonal of a cuboid and a cube. If L, B and H be the length, breadth and height of a cuboid, then diagonal equal to under root L square plus B square plus H square units. In case of a cube, L equal to B equal to H. Therefore, diagonal of a cube equal to under root L square plus L square plus L square equal to under root 3L square equal to under root 3L units. Example: a water tank is 1.4 meter long, 1 meter wide and 0.7 meter deep. How many liters of water can it hold? Solution: length of the tank L equal to 1.4 meter equal to 140 centimeter. Breadth of the tank B equal to 1 meter equal to 100 centimeter. Depth of the tank H equal to 0.7 meter equal to 70 centimeter. Therefore, volume of the tank equal to L into B into H equal to 140 into 100 into 70 centimeters cube equal to 140 into 100 into 70 upon 1000 equal to 980 liters. Hence, the tank can hold 980 liters of water. Note: in case of a cuboid, any of the surfaces can be called the base. The face opposite to the base will be called the top surface. Find the volume and surface area of the cuboids whose dimensions are Find the volume and surface area of the cubes whose edges are multiple choice questions. Chapter 17: Data Handling. Organizing data. Suppose the data collected on favorite sports of 30 students by the teacher is as follows: cricket, tennis, football, cricket, cricket, football, tennis, basketball, cricket, cricket, tennis, cricket, tennis, cricket, cricket, football, football, basketball, basketball, tennis, cricket, basketball, football, tennis, football, cricket, tennis, cricket, tennis, cricket. The data given above is unorganized and cannot be easily interpreted, so it is called raw data. From the above data, it is not easy to answer questions like which is the most popular sport and which is the least popular sport? To quickly answer these questions, we need to organize the given data. We arrange the data in a table using tally marks as shown alongside. The number of tallies against each sport gives the number of students who like that sport. This is known as the frequency of the popularity of that sport. Frequency of cricket is 12, which means that the entry for cricket occurs 12 times in the above data. The above table is called the frequency distribution table as it gives us information regarding the number of times an entry occurs. Using this table, it is easy to answer the questions asked. Grouping data. Consider the following example of marks obtained by 50 students of a school in a competitive examination in mathematics. 36, 65, 47, 39, 52, 68, 76, 79, 80, 56, 76, 45, 38, 23, 26, 67, 78, 46, 76, 56, 58, 46, 75, 69, 58, 46, 53, 55, 58, 72, 66, 48, 54, 44, 63, 56, 57, 71, 51, 65, 79, 46, 55, 56, 51, 54, 38, 39, 76, 80. In this case, if we make a frequency distribution table to accommodate each observation individually, the table would be very long. Hence, we make groups of observations like 0 to 10, 10 to 20, 20 to 30, and so on up to 60 to 70, 70 to 80. These groups are called class intervals. In the class interval 0 to 10, 0 is called the lower class limit and 10 is called the upper class limit. Similarly, in class interval 10 to 20, 10 is called the lower class limit and 20 is called the upper class limit. The difference between the upper class limit and the lower class limit is called the class size or the class width. Remember, the class size is same for all class intervals. In the above example, it is 10. The mid value or class mark of a class interval is obtained by adding its lower class limit and upper class limit and dividing the sum by 2. For example, the class mark of the class interval 20 to 30 is 20 plus 30 upon 2 equal to 25. The range of a data is the difference between the maximum and minimum values. Range equal to maximum marks minus minimum marks. In the above example, the range is 80 minus 23 equal to 57. Using groups or class intervals, the frequency distribution table for the marks of 50 students can be made in the following way. Class interval, tally marks, frequency, 20 to 30, 2, 30 to 40, 5, 40 to 50, 8, 50 to 60, 16, 60 to 70, 7, 70 to 80, 12. Since the data is represented in groups, the above distribution table is called Grouped Frequency Distribution Table. Earnings by different shopkeepers in a month are given in the form of a frequency table. The daily wages of 60 workers in a factory are given in the following frequency distribution table. Double bar graph. A double bar graph is used to show two sets of data simultaneously. It is useful for the comparison of two sets of data as in the following cases. Results of students in different subjects for 2 years are to be shown. Results of a student in different subjects is to be compared with the class average in those subjects. Current sale of the production of a factory is to be compared with the sale of the previous year, either item-wise or month-wise. Double bar graph. A histogram. A histogram is used to represent the data of a grouped distribution table. The histogram shown below is the graphical representation of the given data. Class interval frequency 20 to 30, 2, 30 to 40, 4, 40 to 50, 8, 50 to 60, 17, 60 to 70, 7, 70 to 80, 12. A. The x-axis represents class intervals. B. There is no gap between the bars here, as there is no gap between the class intervals. C. The y-axis represents frequency of individual class intervals. Also, the height of the bars is proportional to the frequency of the corresponding class intervals. Note, in figure, a jagged line or kink has been used along the x-axis to show that we are not starting with the class interval 0 to 10. Remember, the jagged line is to be used only at the starting point to show that we are not starting with 0. Using it to show that we are skipping numbers in the middle is wrong. Pie chart. Data represented in a circular form is called a pie chart or pie diagram or circle graph. A pie chart shows the relationship between a whole and its parts. A whole circle is divided into sectors. The size of each sector is proportional to the information it represents. Pie charts are very popular diagrams used for representing breakdown of a data into its subdivisions. The pie chart shows the musical instruments learnt by 300 students of a school. How many of these students learnt? Chance and probability. Every day, we hear people making statements like, "Take your raincoat to school. It will probably rain today." "All the trains are running late. Your train may also be late." "You have always done well in your exams. Your result will probably be very good this time also." "Our teacher is rarely absent. Chances of her being absent today are nil." People make such statements on the basis of their previous experiences or on the basis of certain studies. The meteorological department also predicts weather on the basis of data collected and trends observed over the years. But the chances of predictions, even if based on well-conducted studies, not coming true always exist. It may rain on the day on which bright sunlight was predicted. A train which was expected to be late may arrive before time. A child who has never done well in any examination may top in his class. Predictions are made on the basis of observations of previous events, but chances and probability of the next event being different will always be there. In the above examples, the chances of a certain event happening or not happening will not always be the same. That is, the chances of raining or not raining are not the same. There are certain events where the chances of an event occurring or not occurring are the same. For example, the tossing of a coin. When we toss a coin, we will either get a head or a tail, though we cannot predict whether we will get a head or tail. One sure thing is that we will definitely get one of the two outcomes. The chance of getting either of them is the same. An operation which can produce some well-defined outcomes is called an experiment. Each outcome or a collection of outcomes make an event. For example, when we toss a coin, getting a head or tail are the two outcomes. But if we want a head, then getting a head is an event. Or, when we cast a dice, getting the numbers 1, 2, 3, 4, 5, 6 are all outcomes. But if we want to get 2 or 4, then getting 2 or 4 will be an event. An experiment in which all possible outcomes are known and the next outcome cannot be predicted in advance is known as a random experiment. For example, tossing of a coin is a random experiment. Head or tail are the two outcomes of this experiment. Both outcomes are equally likely outcomes. Chances of getting a head is 1 out of 2 outcomes, that is 1 upon 2. Chances of getting a tail is also 1 out of 2 outcomes, that is 1 upon 2. Outcomes of an experiment are equally likely if each has the same chance of occurring. Probability of an event equal to number of outcomes that make an event, total number of outcomes of the experiment. Consider the example of throwing a dice marked 1, 2, 3, 4, 5, 6 on its faces, one number on each of its faces. If you throw the die once, what are the outcomes? The outcomes are 1, 2, 3, 4, 5 or 6. That is, there are 6 likely outcomes. What is the probability of getting 2? Probability of getting 2 is 1 out of 6, that is 1 upon 6. Out of the 6 likely outcomes, the probability of getting 2 is 1/6. What is the probability of getting 4? It is same as 2, that is 1/6. What is the probability of getting an even number? There are 3 even numbers, 2, 4 and 6. And the chance of getting any one of them when the dice is thrown once is 3 out of 6. Therefore, probability equal to 3 upon 6 equal to 1 upon 2. What is the probability of getting any number from 1 to 6? If we want any number from 1 to 6, the probability of getting the desired outcome is 6 out of 6. Therefore, probability equal to 6 upon 6 equal to 1. Remember, an experiment is a situation involving chance or probability that leads to results called outcomes. An outcome is a result of a single trial of an experiment. An event is one or more outcomes of an experiment. Probability is the measure of how likely an event is. Multiple choice questions. Chapter 18. Graphs. Coordinate system or Cartesian plane. The position of a point in a plane can be denoted with reference to the axis system. It has a horizontal line, x dash OX, also called x-axis, and a vertical line, y O Y dash, called y-axis. The point of intersection of these two axes is called the origin, denoted by O. X dash OX and y O Y dash taken together are called coordinate axes. The configuration so formed is called a coordinate system or coordinate plane or Cartesian plane. As you may observe, the plane is divided into 4 parts. Each of these parts is termed as quadrant. These quadrants are named as first, second, third, and fourth respectively in anti-clockwise direction. We can summarize the above information as follows. The distances measured along OX and OY are taken as positive. The distances measured along OX' and OY' are taken as negative. Path, quadrant, signs of coordinates, XOY, first, plus plus, YOX', second, minus plus, X', third, minus minus, Y', fourth, plus minus. The location of a point P is denoted as PXY, that is, X is written first and Y later. This denotion is known as ordered pair, where X is called the X coordinate or abscissa and Y is called the Y coordinate or ordinate. The origin is represented as 0, 0. Remember, for any point on x-axis, its ordinate is 0. So the coordinates of any point on x-axis are x, 0. For example, points 3, 0, -7, 0, etc. lie on x-axis. For any point on y-axis, its abscissa is 0. So the coordinate of any point on y-axis are 0, y. For example, points 0, 3, 0, -7, etc. lies on y-axis. Match the coordinates of the points given in column A with the property mentioned in column B. Algebra and graphs. We have already learned to generalize a given situation in previous classes. Here we relate one branch of mathematics to another one, that is, algebra and Cartesian plane. We know that perimeter of a square is given by P equal to 4 into side. Let the side be x and perimeter P be y. Hence the equation becomes y equal to 4x. Let's take some values of x and find the corresponding values of y. If x equal to 0, then y equal to 4 into 0 equal to 0. X equal to 1, then y equal to 4 into 1 equal to 4. X equal to 2, then y equal to 4 into 2 equal to 8. X equal to 3, then y equal to 4 into 3 equal to 12. X equal to 4, then y equal to 4 into 4 equal to 16, and so on. Tabulating the values of x and y, we get x, y, 0, 0, 1, 4, 2, 8, 3, 12, 4, 16. To plot the graph of this situation, we name the coordinates as A, 0, 0, B, 1, 4, C, 2, 8, D, 3, 12, and E, 4, 16. Now plot these points on a graph as shown alongside. We may summarize the rules to plot a graph as follows. Write the relation of x and y as a function or an equation. Find the different values of y corresponding to the values of x. Write the values in tabular form. Plot the points and join them to obtain a graph. Label the x-axis and y-axis with the suitable variables. Linear graphs. A linear graph is obtained when the coordinates join and form a straight line. The general form of a linear graph is represented as y equal to mx plus c, also called a linear function. Hence, y and x are the two variables. M is the coefficient of x, which may take any value depending on the conditions, and C is the constant, also called intercept. Linear graphs are used widely in comparing the results of any two or more events. For example, to compare the performance of two teams in cricket, to compare the performance of two cars of different company. We may find the linear graphs in the newspaper, business magazines, science books, etc. Some of the common linear graphs are distance time graph, speed time graph, temperature time graph, etc. In this section, we shall discuss plotting of distance versus time, speed versus time graphs, reading and interpretation of these graphs. Distance time graph. The graphs used to describe motion of a vehicle such as a cycle, car, train, aeroplane, etc. are called travel graphs or distance time graphs. The distance traveled is represented on y-axis and the time taken on the x-axis. That is, time is an independent variable and distance traveled is a dependent variable. These graphs can be used to find the speed of the vehicle. Let's take an example to understand the topic further. Graph given alongside shows the distance of a cyclist from his home. We may draw the following conclusions from the graph. The cyclist left home at 8 a.m. and returned at 5 p.m. He was 20 km away from home at 10 a.m. At 11 a.m., he was 20 km away from home. This suggests that he took a rest between 10 to 11 a.m. At 1 p.m., he was 45 km away from his home. Speed from 8 a.m. to 10 a.m. equal to distance covered upon time equal to 20 upon 2 equal to 10 km per hour. Speed from 3 p.m. to 5 p.m. equal to distance covered upon time equal to 60 upon 2 equal to 30 km per hour. The sharp slope of the graph between 3 p.m. to 5 p.m. suggests that the cyclist was traveling fastest between 3 p.m. to 5 p.m. Multiple choice questions. Fill in the blanks. Take the correct option from the following.